In 2029, something will pass closer to Earth than our own satellite's orbit. And it is not the interstellar comet everyone is talking about. While 3IATLAS captures headlines with its exotic pedigree and harmless 268 million kilometer flyby, a massive asteroid named Apophis is performing the ultimate cosmic sleight of hand. It is quietly approaching for the closest planetary flyby in recorded human history. In 2029, this 340-meter-wide mountain of rock and metal will pass 10 times closer than the Moon, moving at 7.4 kilometers per second. That is close enough to see with a naked eye. But for some strange reason, we are treating the tourist like a threat and ignoring the neighbor who is actually coming to visit. As we will see tonight, the question is not why we are obsessed with 3IATLAS. It is why we are not talking about Apophis. Part 1. The Visitor. We do not need to fear. Here it comes, streaking through the darkness beyond Mars, trailing a ghostly veil of ice and dust. Comet 3IATLAS, only the third confirmed interstellar object ever discovered, passing through our cosmic neighborhood, will reach its closest point to the Sun around October 30th, 2025. The media calls it an alien visitor. The headlines practically write themselves. But here is the thing about visitors from other star systems. They are polite guests who keep their distance. 3IATLAS will reach approximately 167 million miles from Earth on December 19th. And at no point will it pose a threat. That is nearly 270 million kilometers, a distance so vast that our Moon could fit in that gap 699 times over. Yet somehow, this harmless wanderer has captured more attention than the rocky neighbors that actually share our orbital dance around the Sun. The designation 3I tells us everything we need to know about this cosmic tourist. The I stands for interstellar, meaning this chunk of frozen material is moving on what astronomers call a hyperbolic trajectory. Picture a slingshot motion that carries it past our Sun once, and then flings it back into the void between stars, never to return. It is the ultimate one-night stand of the cosmos. This is not just any old comet, mind you. 3IATLAS marks only the third time in recorded history that an interstellar object has been identified passing through our solar system, following the landmark discoveries of 1I Oumuamua in 2017 and 2I Borisov in 2019. Each of these visitors offers scientists a rare glimpse into the composition of other stellar neighborhoods, frozen time capsules that have wandered the galaxy for millions of years. The Hubble Space Telescope has been tracking 3IATLAS since its discovery, capturing images that reveal a teardrop-shaped dust approaches the Sun. Solar radiation sublimates the frozen gases on its surface, creating that characteristic coma and tail that make comets so photogenic. It is performing exactly as expected. A textbook example of how interstellar comets behave when they encounter the warmth of our star. But here is where the story gets interesting and why you should pay attention to what I am about to tell you. While 3IATLAS commands headlines with its exotic pedigree, there is something much more significant happening in our cosmic backyard. Something that will not make the evening news because it is not mysterious enough, not alien enough, not sufficiently clickable for our short attention spans. The truth is, danger in space is not about rarity. It is about proximity combined with probability. 3IATLAS will reach its closest approach to the Sun around October 30th at a distance of 1.4 astronomical units, about 130 million miles, or 210 million kilometers, just inside the orbit of Mars. That is still comfortably far from Earth's orbit, which sits at 1 astronomical unit from the Sun. The geometry of this flyby means that Earth and 3IATLAS are never even remotely close to occupying the same piece of space. NASA's Planetary Defense Coordination Office, yes, that is a real organization, and we will talk more about them later, has been crystal clear about this. No threat. The European Space Agency echoes the same assessment. Harmless pass. These are not euphemisms or careful bureaucratic language designed to avoid panic. They are mathematical certainties based on orbital mechanics that we have understood since Newton's time. Yet, the visual spectacle continues to unfold. As soon as the comet passes perihelion on October 29th, it will move at its maximum speed, allowing it to become quickly visible again in the early morning sky during the first days of November. Amateur astronomers around the world are preparing their telescopes for what promises to be an impressive show. A genuinely rare opportunity to observe an object that originated in the depths of interstellar space. But while we are all gazing up at this beautiful, harmless visitor, something far more mundane and infinitely more important is happening in the quieter corners of astronomical research. Teams of scientists are tracking objects that do not make headlines, objects that follow more conventional orbits, objects that share our immediate cosmic neighborhood. These are the near-Earth asteroids, or NEAs, as the professionals call them. They do not come from exotic places between the stars. They formed right here in our own solar system, in the same disk of dust and debris that gave birth to Earth itself. There are siblings, cosmically speaking, and some of them follow orbital millions of kilometers while largely ignoring the chunks of rock and metal that regularly pass within the Moon's orbital distance. The closest approach of Comet 3IATLAS to Earth will happen on Friday, December 19th, 2025. At a distance of 1.797 astronomical units, or 268 million kilometers. Compare that to the dozens of small NEOs that pass within 400,000 kilometers, the distance to our Moon, every single year. The difference in media coverage is telling. Interstellar objects get the visitor from another star treatment, complete with speculation about alien origins and mysterious compositions. Near-Earth asteroids get buried in technical journals and NASA press releases that most people never read. Yet, which category actually poses a measurable risk to our planet? The answer should be obvious, but somehow it is not. 3IATLAS will provide valuable scientific data about the composition of materials from other stellar systems. It might tell us something about how comets form in different environments, how they weather during their long journeys through interstellar space. This information could refine our understanding of planetary formation and the distribution of organic compounds throughout the galaxy. All fascinating stuff for researchers. What 3IATLAS will not do is teach us anything about planetary defense. It will not help us prepare for the kinds of impacts that have shaped Earth's history. The Chicxulub asteroid that ended the age of dinosaurs, the Tunguska event that flattened 2,000 square kilometers of Siberian forest, the Chelyabinsk meteor that injured over 1,000 people in 2013. Those events involved objects that were already part of our solar system, following predictable orbits that could, in theory, have been tracked years or decades in advance. The asteroid that will concern us next, the one that keeps planetary defense experts awake at night, will not be an exotic visitor from Alpha Centauri. It will be a perfectly ordinary chunk of rock or metal that happens to be on a collision course with the only planet we have got. So, while 3IATLAS puts on its spectacular light show, racing toward perihelion at over 40 kilometers per second, remember this. The real threats are often hiding in plain sight. They do not announce themselves with glowing comas or hyperbolic trajectories. They are just there, quietly following their elliptical orbits, waiting for that one moment when gravity and geometry align in precisely the wrong way. But before we get to that story, before we meet the asteroid that actually did scare the experts, we need to understand what 3IATLAS is really teaching us about risk, probability, and the difference between spectacular and dangerous. Part 2, 3IATLAS, what it teaches and what it does not. Let us talk about what makes 3IATLAS genuinely remarkable from a scientific perspective, and why that remarkableness has absolutely nothing to do with planetary defense. The interstellar comet's size and physical properties are being investigated by astronomers around the world. Early observations suggest a nucleus that is at most a few kilometers across, potentially smaller than many of the asteroids we routinely track in Earth's vicinity. The Hubble Space Telescope has placed an upper limit of about 5.6 kilometers on its diameter, though the actual size could be significantly smaller once we account for the brightness contributed by its expanding coma. What makes 3IATLAS scientifically valuable is not its size or its trajectory. It is its composition. This object spent millions, possibly billions of years drifting through the void between stars, subjected to cosmic radiation and the frigid temperatures of deep space. Any organic compounds it carries, any clues about the stellar system where it originated, any insights into how comets survive the journey between stars. These are the treasures that astronomers are racing to capture before it disappears forever. The James Webb Space Telescope is contributing spectroscopic data that could reveal the chemical fingerprints of 3IATLAS's home system. Ground-based observatories are measuring the polarization of reflected sunlight to understand the texture and composition of dust grains in its coma. Radio telescopes might detect emissions from specific molecules as they sublimate from the nucleus. It is a coordinated global effort to squeeze every bit of information from this fleeting opportunity. But here is what 3IATLAS absolutely cannot teach us: how to respond to a genuine impact threat. The geometry of its orbit places it permanently in the interesting, but irrelevant, category for planetary defense. At no point will it pose a threat, and not just because of its current trajectory. The fundamental physics of interstellar objects makes them poor candidates for impact scenarios. They are moving too fast on paths too steep, with closest approaches that are measured in astronomical units rather than Earth radii. Compare this to the objects that planetary defense experts actually worry about. Near-Earth asteroids follow elliptical orbits that intersect or come close to Earth's orbital path. They return periodically, sometimes every few years, sometimes every few decades or centuries. Most importantly, their orbital characteristics can change over time due to gravitational perturbations from the planets, solar radiation pressure, or the subtle but measurable Yarkovsky effect, the recoil force created when an asteroid absorbs sunlight and re-radiates it as heat. This is where the mathematics of risk assessment becomes crucial, and where media coverage often goes astray. Danger, cosmic equivalent of a beautiful but completely safe fireworks display. All spectacle, no substance when it comes to actual hazard. The media narrative around 3IATLAS follows a predictable pattern that we have seen with previous interstellar visitors. First comes the breathless announcement of discovery. Alien visitor from another star. Then, the obligatory safety disclaimer buried in paragraph 7. No threat to Earth. Then, weeks of speculation about its mysterious origins and exotic composition. What is missing from this coverage is any meaningful discussion of the objects that actually do pose measurable risks. The near-Earth asteroids that pass within lunar distance every few weeks. the potentially hazardous asteroids, PHAS, that are large enough and close enough to warrant continuous monitoring. The statistical reality that somewhere out there, on an orbit we have not fully characterized yet, there is likely an object with Earth's name on it. NASA's Center for Near-Earth Object Studies maintains detailed trajectory calculations for thousands of known NEAs. Their close approach tables show a steady stream of small asteroids passing nearby. Objects with names like 2024P T5 or 2025R X12 that never make headlines because they are neither mysterious nor dangerous enough to capture public attention. These are the objects that matter for planetary defense, because these are the objects we might actually need to deflect someday. Understanding how to change the trajectory of a near-Earth asteroid requires detailed knowledge of its internal structure, surface composition, rotation rate, and response to external forces. 3IATLAS, racing past at dozens of kilometers per second, on its way back to interstellar space, offers none of these insights. The DART mission, NASA's Double Asteroid Redirection Test, demonstrated kinetic impact deflection by crashing into the asteroid moon Dimorphos in 2022. The mission succeeded beyond expectations, changing Dimorphos's orbital period by 32 minutes instead of the minimum 10 minutes needed to declare success. But DART targeted a near-Earth asteroid system, not an interstellar visitor, because near-Earth asteroids are the objects we might actually need to deflect. The upcoming Hera mission, launched by the European Space Agency in October 2024, will arrive at the Didymos Dimorphos system in late 2026 to study the aftermath of DART's impact in detail. Again, this mission focuses on near-Earth asteroids, because that is where the actionable planetary defense knowledge lies. 3IATLAS will contribute exactly 0 data points to our understanding of asteroid deflection techniques. Its hyperbolic trajectory means it is essentially in free fall past the Sun, immune to the kinds of gravitational perturbations that govern the long-term evolution of near-Earth object that is already leaving the solar system at escape velocity. This brings us to a crucial point about risk communication and public perception. The exotic and the dangerous are not the same thing. 3IATLAS captures our imagination precisely because it is alien in the most literal sense. A visitor from the space between stars carrying potential clues about planetary formation in distant stellar systems. But imagination and risk assessment operate on completely different wavelengths. The objects that should keep us awake at night are the ordinary ones. The S-type asteroids, composed of silicate rock and nickel-iron metal. The C-type asteroids, rich in carbon compounds and water. The Q-type asteroids, that might be fragments of larger bodies shattered by ancient collisions. These pedestrian classifications represent the actual threats, because these are the objects that share our orbital neighborhood. From now through the beginning of September, Comet 3IATLAS will be in the evening sky. For the rest of September and October, it will be too close to the Sun to see. But by November and December, the comet will be bright after just passing the Sun, and also out of the Sun's glare. This observing timeline perfectly illustrates why interstellar objects make poor case studies for planetary defense. They appear, provide a brief window for observation, then disappear forever. Near-Earth asteroids, by contrast, return on predictable schedules. We can observe them during multiple apparitions, track how their orbits evolve over time, and build the detailed physical models needed for deflection mission planning. They're the reliable neighbors whose behavior we can study and predict, unlike the exotic tourists who blow through once and never return. So enjoy the show that 3IATLAS is about to provide. Marvel at humanity's ability to detect and track objects from interstellar space. Appreciate the international cooperation that makes these observations possible. But remember that the real work of planetary defense happens in the mundane cataloging of ordinary asteroids following predictable orbits. Because, while we're watching the beautiful visitor that poses no threat, the objects that actually matter are quietly going about their business, following the same elliptical paths they followed for millions of years, occasionally passing uncomfortably close to home. Part 3. Reframing risk. Known neighbors versus rare visitors. The universe operates on a simple principle that humans consistently misunderstand. Familiarity breeds safety, but also complacency. The objects that threaten Earth aren't the mysterious visitors from distant stars. They're our own neighbors, following predictable paths through a shared gravitational neighborhood. Let's establish the taxonomy of things that actually matter. Near Earth, that's roughly 200 million kilometers, close enough to intersect or approach Earth's orbital path. Within this category, astronomers recognize 4 distinct families based on their orbital characteristics. The Aten group orbits primarily inside Earth's path, with semi-major axes less than 1 astronomical unit, but aphelion distances greater than 0.983 AU. These asteroids spend most of their time closer to the Sun than we are, but their elliptical orbits still carry them across our path. The Apollo group follows orbits that cross Earth's trajectory, with semi-major axes greater than 1 astronomical unit, but perihelion distances less than 1.017 AU. The Amor group approaches from outside Earth's orbit, with perihelion distances between 1.017 and 1.3 AU. Finally, the Atira group orbits entirely inside Earth's path, though a few members can still approach our planet during their most distant excursions. Within these families lurk the potentially hazardous asteroids, PHAS, defined by 2 criteria that sound deceptively technical, but translate to something quite straightforward. They're big enough to cause serious damage if they hit, and their orbits bring them close enough to matter. Specifically, a PHA has a minimum orbital intersection distance with Earth of less than 0.05 astronomical units, about 7.5 million kilometers, and an absolute magnitude of 22 or brighter, corresponding to a diameter of roughly 140 meters or larger. That size threshold isn't arbitrary. An asteroid 140 meters across carries enough kinetic energy to devastate a major metropolitan area. We're not talking about extinction-level events. Those require objects at least a kilometer in diameter, but regional disasters that could kill millions and disrupt global civilization for years. The Chelyabinsk meteor of 2013 was only about 20 meters across, and still managed to injure over 1,500 people with its shockwave. Scale that up by a factor of 7 in diameter, and you're looking at a very different kind of problem. NASA analysis confirms Earth is safe from asteroid Apophis for 100+ years. But this reassuring statement applies to just one specific object. The broader population of PHAS contains over 2,000 known members, with new discoveries added regularly as our surveys improve. Each one represents a potential future headline, a possible intersection of trajectory and timing that could spell disaster for some unlucky portion of our planet. The discovery curve for near-Earth asteroids tells a story of accelerating awareness. In 1990, we knew of fewer than 200 NEAs. By 2000, that number had grown to over 1,000. Today, we've cataloged more than 34,000, with roughly 3,000 new discoveries each year. Global catastrophes are mostly accounted for. We found an estimated 90% or more of the kilometer-class NEAs, and none of them pose any near-term threat. But the smaller objects, the city killers in the 100 to 500 meter range, remain largely undiscovered. Current estimates suggest there are still tens of thousands of these objects waiting to be found. Each one a potential regional disaster if it arrives at the wrong time and place. The upcoming NEO Surveyor mission, an infrared space telescope optimized for asteroid hunting, should dramatically improve our detection rate for these dark, hard-to-see objects when it launches no earlier than late 2027. Here's where the statistics become both reassuring and unsettling. On any given day, multiple small near-Earth asteroids pass within the Moon's orbital distance. These close approaches happen so frequently that NASA maintains automated systems to calculate and publish the details without human intervention. Most are tiny objects that would burn up harmlessly in our atmosphere. But occasionally something larger slips through our detection net and reminds us of the gaps in our knowledge. The frequency of these encounters illustrates a crucial point about asteroid risk. It's not about individual probabilities, but cumulative exposure over time. Each close approach represents a very small chance of impact, but those small chances add up over centuries and millennia. The objects we track today might miss us by comfortable margins, but their orbits are slowly evolving due to gravitational perturbations and non-gravitational forces like the Yarkovsky effect. This is where 3IATLAS becomes not just irrelevant, but actively misleading as a case study in space hazards. Its hyperbolic trajectory means it's essentially immune to the gravitational influences that govern the long-term evolution of near-Earth asteroid orbits. It will never return, never accumulate multiple close approaches, never gradually drift from a safe orbit into a dangerous one. It's a one-time event with zero cumulative risk. Near-Earth asteroids, by contrast, are persistent threats that evolve over time. An asteroid that passes safely today might return decades later on a slightly different trajectory. The gravitational influence of the planets, particularly Jupiter, can reshape NEA orbits over relatively short astronomical timescales. What appears safe based on current orbital calculations might not remain safe indefinitely. The Yarkovsky effect adds another layer of complexity. Named after the Russian civil engineer who first described it, this phenomenon occurs when an asteroid absorbs sunlight during its day and re-radiates that energy as heat during its night. The asymmetric emission of thermal photons creates a tiny but persistent rocket-like force that can gradually alter the asteroid's orbit over thousands of years. For small asteroids, this effect can be significant enough to move from safe trajectories into impact courses, or vice versa. Detecting and measuring the Yarkovsky effect requires years of precise astrometric observations, exactly the kind of long-term monitoring that's impossible for interstellar visitors, but essential for near-Earth asteroid risk assessment. We need to track these objects through multiple apparitions, measuring tiny changes in their positions relative to background stars, building up the observational baseline needed to detect orbital drift. This is unglamorous work that rarely makes headlines. No dramatic discoveries of alien visitors, no exotic compositions hinting at distant stellar nurseries, just the patient accumulation of positional measurements, the gradual refinement of orbital models, the slow but steady progress toward a complete census of objects that might actually pose a threat. The contrast couldn't be starker. 3IATLAS commands international attention for a few months as it sweeps through our solar system, generating papers about interstellar composition and planetary formation processes in alien systems. Meanwhile, teams of dedicated astronomers spend decades tracking ordinary near-Earth asteroids, building the knowledge base that might someday save our civilization from an impact that would make Chelyabinsk look like a firecracker. The irony runs deeper than media coverage. Our fascination with exotic visitors from interstellar space actually demonstrates how well our planetary defense systems work for the threats that matter. We can afford to treat 3IATLAS as pure science, a fascinating but harmless curiosity, precisely because we've developed the infrastructure to distinguish between spectacular and dangerous. But that infrastructure exists only because previous generations of astronomers took the unglamorous threats seriously. They built the surveys that catalog near-Earth asteroids, developed the computational tools that predict orbital evolution, established the international cooperation networks that coordinate observations and share data. They understood that the real enemy isn't the unknown visitor, but the familiar neighbor whose behavior we haven't quite pinned down yet. Which brings us to the object that taught us most of what we know about asteroid risk communication, orbital uncertainty, and the difference between scary headlines and actual danger. An asteroid discovered in 2004 that briefly held the record for highest impact probability ever calculated. An object whose story illuminates everything we've discussed about the difference between interstellar visitors and near-Earth neighbors. Its name is Apophis, and its tale of transformation from existential threat to scientific opportunity reveals everything you need to know about how planetary defense really works. Part 4. Meet Apophis, From Scare to Science. June 19, 2004. A routine night at the Kitt Peak National Observatory in Arizona, where astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi were conducting a systematic search for near-Earth asteroids. Their images revealed a faint moving point of light, unremarkable in appearance, but following a trajectory that would soon make it the most closely watched asteroid in the world. They designated it 2004 MN4, a temporary identifier that would later give way to the official name, 99,942 Apophis, after the ancient Egyptian serpent, god of chaos and destruction. The name would prove prophetic, though not in the way anyone expected. Initial orbital calculations based on just a few nights of observations suggested something alarming. This was no ordinary near-Earth asteroid, following a comfortable path around the Sun. Apophis appeared to be on a collision course with Earth, with impact predicted for April 13, 2029. The probability wasn't trivial. Early estimates put the chance of impact at nearly 3%, higher than any previously calculated for a known asteroid. By December 2004, they had enough data to make a rough calculation of the future orbit of the asteroid, and they found it had a 2.7% chance of hitting the Earth in April 2029, on Friday the 13th. The cosmic timing seemed almost deliberately ominous. An asteroid named after the god of chaos, threatening to arrive on the most superstitious date on the calendar. That 2.7% probability earned Apophis a level 4 rating on the Torino scale, the highest ever assigned to a known object at that time. The Torino scale runs from 0 to 10, with 0 representing no collision hazard, and 10 indicating certain collision with global consequences. Level 4 sits squarely in the yellow, meriting attention by astronomers category. But it was unprecedented for a real object with a specific impact date. The astronomical community mobilized with an intensity rarely seen outside of major space missions. Observatories around the world began tracking Apophis whenever it was visible, accumulating the additional measurements needed to refine its orbital path. The European Space Agency's Space Situational Awareness Program made Apophis tracking a priority. NASA's Near-Earth Object Program expanded its observations and analysis efforts. What they found over the following months illustrates everything important about asteroid risk assessment and why early scary numbers should never be mistaken for final outcomes. Additional observations revealed that Apophis is an S-type asteroid, a stony composition of silicate rock and nickel-iron metal, with an elongated shape roughly 340 meters long and 150 meters wide. Its dark surface reflects only about 23% of the sunlight that hits it, making it relatively difficult to detect, despite its substantial size. Radar observations from the Arecibo Observatory and Goldstone Deep Space Communications Complex reveal details about its shape, rotation, and surface properties. The size estimate carried sobering implications. An object 340 meters across, moving at typical asteroid impact velocities, would release energy equivalent to several hundred megatons of TNT, roughly 10 times the yield of the largest nuclear weapon ever tested. This wouldn't be an extinction-level event like the Chicxulub impact that ended the age of dinosaurs, but it would represent a national-scale disaster, potentially killing millions of people and disrupting global civilization for years. But size and energy calculations were getting ahead of the more fundamental question. Would Apophis actually hit Earth at all? Each new observation helped narrow the uncertainty in its predicted trajectory, and those uncertainties were shrinking faster than the nominal impact probability was holding steady. The breakthrough came from an unexpected source. Don Yeomans and his team at NASA's Jet Propulsion Laboratory realized they needed to account for pre-discovery observations of Apophis images taken before its formal discovery that showed the asteroid as an unrecognized dot among the stars. By mining archival sky survey data, they found observations of Apophis dating back to March 2004, extending the observational arc and dramatically improving their ability to predict its future path. NASA analysis confirms Earth is safe from asteroid Apophis for 100+ years, but this reassuring conclusion emerged gradually over several years of increasingly precise observations. The 2005 apparition, when Apophis was most favorably placed for ground-based telescopes, provided the crucial data needed to rule out the 2029 impact. By 2006, refined calculations had reduced the impact probability to effectively zero. The asteroid would indeed make an extremely close approach to Earth on April 13, 2029, but it would miss by a comfortable margin of about 32,000 kilometers, close enough to pass between Earth and the geostationary satellite belt, but with no danger to Earth, to anyone or anything living on it, or to astronauts or satellites in space. Yet, even with the 2029 impact ruled out, Apophis continued to hold astronomers' attention due to the concept of gravitational keyholes, tiny regions in space through which the asteroid would need to pass during its 2029 flyby to set up a subsequent impact in 2036 or later dates. These keyholes are extraordinarily narrow, typically only a few hundred meters wide, but they represent the mechanism by which a close but safe encounter can evolve into an eventual collision. The keyhole for a 2036 impact was particularly concerning because early calculations couldn't definitively rule out passing through it. The asteroid's trajectory would carry it close enough to this region that measurement uncertainties prevented a confident, all-clear assessment. For several years, Apophis retained a non-zero probability for 2036 impact, though much lower than the original 2029 calculation. The final piece of the puzzle required detecting and measuring the Yarkovsky effect on Apophis, the subtle orbital drift caused by asymmetric thermal emission. This demanded extraordinary precision in astrometric measurements, tracking the asteroid's position relative to background stars to an accuracy of a few hundredths of an arcsecond over multiple years. The detection came in 2021, when independent teams confirmed that Apophis was indeed drifting away from a purely gravitational orbit due to the Yarkovsky effect. The measured drift was small, about -70 meters per year in the semi-major axis, but it was enough to rule out passage through the 2036 keyhole and eliminate the residual impact risk for over a century. This progression from scare to certainty illustrates how planetary defense is supposed to work. Early observations with large uncertainties generate alarming impact probabilities. Additional data gradually shrinks those uncertainties. Eventually, measurements become precise enough to confidently rule out impact scenarios, at which point the asteroid transitions from potential threat to scientific opportunity. Apophis never stopped being dangerous in the abstract sense. It's still a city-killer-sized object that passes uncomfortably close to Earth, but it stopped being a specific date threat once we accumulated enough observational data to predict its behavior with confidence. The difference between abstract danger and specific threat is measured in the precision of orbital calculations. The story also reveals how asteroid scares should be communicated to the public. The initial 2.7% probability was real, not a mistake or false alarm, but the best estimate available given limited data. As observations accumulated and uncertainties shrank, that probability dropped to effectively zero. This pattern of high initial uncertainty converging to confident prediction represents the scientific process working exactly as intended. The closest known approach of Apophis will occur on April 13, 2029, at 21:46 Universal Time, when Apophis will pass Earth at a distance of about 31,600 kilometers above the surface. What was once humanity's most precisely predicted doomsday has become our most precisely predicted astronomical spectacular. A transformation that tells us everything we need to know about the difference between uncertainty and danger. But the story of Apophis doesn't end with its rehabilitation from threat to curiosity. In fact, the most interesting chapter is just beginning. Part 5. Why 2029 matters anyway. Asteroid Apophis will safely pass close to Earth on April 13th. 2029 at 10 times closer than the Moon. Safe, yes, but still the most significant asteroid encounter in recorded human history. Picture this. Apophis will make a very close approach to Earth on April 13th, 2029, when it will pass less than 32,000 kilometers from Earth's surface, just inside the orbiting distance of geosynchronous satellites. For context, our geostationary communications satellites orbit at 35,786 kilometers altitude. Apophis will thread the needle between Earth and this critical infrastructure, following a trajectory that no object of comparable size has ever taken in the modern era. The date itself carries an almost mythical significance. April 13th, 2029, a Friday the 13th that will be remembered not for superstition, but for science. Weather permitting and depending on your location on Earth, you might actually see Apophis with the naked eye as it races across the night sky. For observers in parts of Europe, Africa, and Western Asia, this 340-meter chunk of rock and metal will appear as a moving star visible without telescopes for the first time since its discovery 25 years earlier. But visibility is just the beginning of what makes this encounter extraordinary. At this distance, Earth's gravity will have a notable impact on the passing space rock, altering its orbital characteristics and possibly its physical properties. We're not just watching Apophis, we're participating in a natural experiment in celestial mechanics that will play out in real time before a global audience of professional and amateur astronomers. Earth's gravitational field will stretch and compress Apophis as it passes through our vicinity, creating tidal forces similar to what our planet experiences from the Moon, but compressed into a flyby lasting just a few hours. These forces may trigger what planetary scientists call seismic activity. Not earthquakes in the conventional sense, but mechanical stress that could reshape the asteroid's surface, trigger landslides among loose surface material, and potentially alter its rotation rate. The current best estimates suggest Apophis rotates once every 30.6 hours. A leisurely tumble that may change significantly during the encounter. Earth's gravity could either speed up or slow down this rotation, depending on the complex interplay between the asteroid's shape, internal structure, and the exact geometry of its closest approach. Predicting these changes requires sophisticated computer models that account for Apophis's elongated shape and likely rubble pile internal structure. That internal structure matters more than you might expect. Most asteroids aren't held together by their own weak gravity. Think of a bag of gravel rather than a granite boulder. When tidal forces stretch and squeeze such an object, the response depends critically on how tightly the individual components are bound together. If Apophis is relatively coherent, more like fractured bedrock than loose rubble, it might emerge from the encounter relatively unchanged, except for its altered orbit and rotation. If it's a loose aggregate barely held together by gravity, the tidal stress could trigger significant surface changes, exposing fresh material that's been protected from solar radiation and micrometeorite bombardment for millions of years. The timing of maximum tidal stress will occur at precisely 21 hours, 46 minutes, universal time, on April 13th, when Apophis passes closest to Earth. At that moment, our planet will exert gravitational forces on the asteroid roughly 50 times stronger than what it experiences from its own self-gravity. For a rubble pile structure, this represents a genuine test of mechanical integrity. Ground-based radar systems will play a crucial role in documenting these potential changes. The Goldstone Solar System radar in California and the Green Bank Radio Telescope in West Virginia can achieve meter-level resolution of Apophis during its close approach, potentially revealing details about surface texture, boulder distribution, and any landslides or reshaping triggered by tidal forces. Optical telescopes around the world will monitor changes in brightness and color that might indicate freshly exposed subsurface material. If tidal stress does trigger significant landslides, astronomers might observe subtle changes in how Apophis reflects sunlight, slightly different colors or brightness patterns that reveal material composition previously hidden beneath space-weathered surfaces. The Catalina Sky Survey and linear asteroid tracking programs will coordinate observations to measure precise changes in Apophis's rotation period and pole orientation. Even small changes in these parameters could provide insights into the asteroid's internal structure and mechanical properties, information that's crucial for designing potential deflection missions for future threats. But perhaps most significantly, the 2029 encounter represents an unprecedented opportunity for public engagement with planetary science. Unlike most astronomical events that require specialized equipment or perfect viewing conditions, Apophis will be bright enough for naked-eye observation from populated areas across much of the Eastern Hemisphere. Amateur astronomers worldwide are already planning coordinated observation campaigns. The International Astronomical Union's Minor Planet Center will coordinate data collection from professional and amateur observers alike, creating a global data set of Apophis's behavior during its close encounter with Earth. Educational institutions are developing curriculum materials around the flyby, using Apophis as a case study in orbital mechanics, gravitational physics, and asteroid science. The encounter offers a rare chance to demonstrate concepts like tidal forces, orbital dynamics, and planetary defense in real time, with a visible, tangible example. For satellite operators, the encounter presents both an opportunity and a challenge. While there's no credible risk of collision with existing satellites, the orbital mechanics are well understood and carefully monitored. The passage of such a large object through the geostationary belt region will require careful tracking and potential minor adjustments to spacecraft operations. The European Space Agency has already indicated they'll use the encounter as a test case for space situational awareness protocols, treating it as a valuable exercise in tracking large objects through critical orbital regions. These procedures could prove useful for future asteroid encounters or for managing the growing population of space debris in Earth orbit. Climate scientists are interested in whether Apophis's passage might trigger detectable changes in Earth's upper atmosphere. While the asteroid won't pass through our atmosphere, its gravitational influence could theoretically cause minute perturbations in atmospheric density at extreme altitudes. Effects so small they'd be undetectable without sensitive instruments, but scientifically interesting nonetheless. The timing also coincides with an active period for space exploration more broadly. Multiple Mars missions, lunar exploration programs, and deep space observatories will be operational during Apophis's flyby, potentially providing additional perspectives on the encounter from various vantage points throughout the solar system. Most importantly, the 2029 flyby transforms Apophis from a former threat into a natural laboratory for understanding asteroid behavior under extreme conditions. Every measurement we make, every change we document, every model we validate contributes to our knowledge base for planetary defense. The next potentially threatening asteroid we discover might share similar characteristics with Apophis, and our observations during the 2029 encounter could prove crucial for planning an effective response. But we won't just be watching from the ground. NASA has repurposed one of its most successful asteroid missions to rendezvous with Apophis after its close encounter with Earth, setting up what promises to be one of the most detailed asteroid studies ever conducted. The story of how OSIRIS-REx became OSIRIS-APEX reveals just how seriously the scientific community takes this once-in-a-lifetime opportunity. Part 6. The Post-Flyby Rendezvous. Sometimes the universe provides perfect timing. As Apophis prepares for its historic flyby of Earth in 2029, NASA has positioned one of its most capable spacecraft to witness the aftermath firsthand. OSIRIS-APEX represents one of the most ambitious repurposing projects in space exploration history. Originally known as OSIRIS-REx, this spacecraft spent 2 years studying the asteroid Bennu, collected samples from its surface in 2020, and successfully delivered those samples to Earth in September 2023. Rather than retire this proven asteroid explorer, NASA extended its mission and retargeted it toward Apophis, creating an unprecedented opportunity to study an asteroid before and after a major gravitational encounter. The spacecraft will arrive at Apophis in June 2029, approximately 2 months after the asteroid's close pass by Earth. This timing is crucial, close enough to the encounter to observe any changes triggered by tidal forces, but far enough removed to allow for safe operations around a potentially altered asteroid. OSIRIS-APEX will then spend approximately 18 months conducting the most detailed study of an asteroid ever undertaken by a spacecraft operating in deep space. The mission's science objectives read like a planetary defense wish list. First priority: document any orbital or rotational changes caused by Earth's gravitational influence. Ground-based observations can measure these changes from afar, but OSIRIS-APEX will provide the precision needed to understand exactly how Earth's gravity modified Apophis's trajectory and spin state. The spacecraft carries a suite of instruments originally designed for asteroid characterization that will prove invaluable for post-encounter analysis. The OCAMS imaging system can resolve surface features down to centimeter scales, potentially revealing whether tidal stress triggered landslides, boulder movement, or other surface modifications. The OTES thermal emission spectrometer will map temperature variations across Apophis's surface, looking for thermal signatures that might indicate freshly exposed subsurface material. Most intriguingly, OSIRIS-APEX will attempt a maneuver that its predecessor never tried at Bennu. I understand you want me to translate to English, but I notice the text is already in English. Since it's already in the target language, I'll correct any spelling errors and convert numbers to words as requested. a powered descent to within approximately 25 meters of Apophis's surface, followed by a thruster firing designed to disturb and loft surface material. This sample site reconnaissance won't involve physical contact with the asteroid Osiris. Apex lacks the touch-and-go sampling arm that enabled OSIRIS-REx to collect material from Bennu, but the thruster blast should expose subsurface composition for remote analysis. The thruster maneuver represents a calculated risk that illustrates how much confidence mission planners have in OSIRIS-Apex's capabilities. Operating at such close range to a potentially modified asteroid requires precise navigation and real-time hazard assessment. If tidal forces did trigger significant surface changes during the Earth flyby, Apophis might present a more hazardous operating environment than originally anticipated. The spacecraft's ability to adapt to changed conditions will be tested immediately upon arrival. OSIRIS-Apex will need to characterize Apophis's post-encounter gravitational field, rotation state, and surface properties before attempting close proximity operations. This represents a unique challenge in spacecraft operations. Most asteroid missions study pristine targets with well-characterized properties, while OSIRIS-Apex will encounter an asteroid that has potentially undergone recent modification. Navigation around Apophis will require extraordinary precision. The asteroid's elongated shape and relatively rapid rotation create a complex gravitational environment even under normal circumstances. If Earth's tidal forces altered the rotation rate or axis orientation, mission planners will need to update their operational procedures in real time, based on OSIRIS-Apex's initial observations. The scientific payoff could be enormous. By comparing pre-flyby ground-based observations with post-flyby spacecraft data, researchers will gain unprecedented insights into how asteroids respond to strong gravitational perturbations. This information directly applies to planetary defense scenarios, where we might need to predict how a threatening asteroid would behave if deflected by a kinetic impactor or gravitational tractor. The mission will also validate computational models used to simulate asteroid deflection missions. Current models make assumptions about asteroid internal structure, surface properties, and mechanical response to external forces. OSIRIS-Apex observations of Apophis's actual behavior during and after its Earth encounter will provide ground truth for these simulations. From an engineering perspective, the OSIRIS-Apex mission demonstrates remarkable spacecraft longevity and adaptability. By the time it reaches Apophis, the spacecraft will have been operating in deep space for over a decade, far exceeding its original design life. The successful extension of OSIRIS-REx into OSIRIS-Apex provides a template for future missions that could potentially visit multiple targets during extended operational phases. The coordination between ground-based and space-based observations during the Apophis encounter will set new standards for international scientific cooperation. Radar facilities, optical telescopes, and space-based infrared observatories will work in concert with OSIRIS-Apex to create the most comprehensive data set ever assembled for a single asteroid. The mission timeline reflects careful planning around astronomical constraints and operational considerations. OSIRIS-Apex's arrival in June 2029 allows enough time for Apophis to move away from Earth's gravitation. The 18-month operational phase provides multiple opportunities to observe Apophis under different lighting conditions and orientations. Data collection will focus on several key parameters that matter for planetary defense applications. Surface roughness and boulder distribution affect how momentum transfer occurs during kinetic impact missions. Internal structure and mechanical properties determine how an asteroid responds to deflection attempts. Composition and thermal properties influence the effectiveness of various deflection techniques. The thruster disturbance experiment deserves special attention as a proof of concept for future missions. By documenting how Apophis surface material responds to artificial disturbance, OSIRIS-APEX will provide insights into regolith properties that could inform the design of more aggressive deflection techniques. If surface material proves loosely bound and easily disturbed, that knowledge could influence decisions about kinetic impactor design or alternative deflection methods. Perhaps most importantly, OSIRIS-APEX will demonstrate that asteroid characterization missions can be extended and repurposed to address planetary defense questions. The spacecraft's original mission to Bennu focused primarily on understanding asteroid composition and formation processes. Its extended mission to Apophis explicitly targets planetary defense applications, showing how basic science and applied research can complement each other in asteroid exploration. The mission will also serve as a pathfinder for future asteroid rendezvous operations in the era of expanded planetary defense activities. As near-Earth asteroid surveys identify more potential threats, the space agencies may need to dispatch characterization missions on relatively short notice. OSIRIS-APEX's operational experience at Apophis will inform the design and procedures for such rapid response missions. Public engagement opportunities abound for the OSIRIS-APEX mission. Unlike most deep space missions that study distant or obscure targets, Apophis will be familiar to the public through its 2029 Earth flyby. The spacecraft's detailed follow-up study provides a natural continuation of the story, maintaining public interest in asteroid science and planetary defense beyond the initial flyby excitement. The mission's data will likely influence asteroid risk assessment methodologies for decades to come. Current impact hazard calculations rely on statistical models of asteroid properties derived from limited observational data. OSIRIS-APEX will provide the kind of detailed ground truth measurements needed to validate and refine these models, potentially improving our ability to assess threats from newly discovered asteroids. But even as OSIRIS-APEX prepares for its rendezvous with post-flyby Apophis, the broader story of planetary defense continues to evolve. The transformation of Apophis from existential threat to scientific opportunity illustrates both the power and limitations of our current approach to asteroid risk assessment. Understanding how we got the risk calculations wrong and then right reveals everything about the difference between uncertainty and danger, and why communication matters as much as computation. Part 7. How we got the risk wrong then right. December 27, 2004. Stephen Chesley at NASA's Jet Propulsion Laboratory ran the numbers one more time, hoping he'd made an error. He hadn't. Based on just 74 observations spanning 64 days, orbital calculations showed that asteroid 2004 MN4, soon to be named Apophis, had a 2.7% chance of striking Earth on April 13, 2029. 2.7% might sound small, but in the context of asteroid impact probabilities, it was astronomical. For comparison, your lifetime odds of being struck by lightning are roughly 1 in 15,000, about 0.007%. Apophis, at that moment, appeared over 300 times more likely to hit Earth than you are to be zapped by lightning in your entire life. The calculation earned Apophis a level 4 rating on the Torino scale, the first time any real asteroid had achieved such a high threat assessment. The Torino scale, developed by MIT's Richard Binzel and named after a 1999 conference in Turin, Italy, ranks asteroid impact threats from 0 to 10. Most objects rate 0, no collision hazard. Apophis briefly held the record at 4, indicating a close encounter meriting attention by astronomers with a non-trivial chance of regional devastation. But here's the crucial point that media coverage consistently missed. That 2.7% wasn't a prediction of doom. it was a measurement of uncertainty. Early orbital calculations for newly discovered asteroids are notoriously imprecise because they're based on limited observational data. Imagine trying to predict where a thrown baseball will land after watching it for only the first few milliseconds of flight. You might be wildly wrong about the eventual impact point, even if your physics is perfect. The same principle applies to asteroid orbits, except the throw happened millions of years ago, and the landing won't occur for decades in the future. Every asteroid observation, a measurement of position against background stars at a specific time, helps constrain the object's orbital parameters. But early in the observational arc, when you have only a few dozen measurements spanning a few weeks or months, the uncertainties remain enormous. Small errors in individual observations can translate to huge uncertainties in future positions. Apophis illustrated this principle perfectly. Those initial 74 observations scattered across just 64 days in mid to late 2004 were insufficient to pin down the asteroid's orbit with the precision needed for confident long-term predictions. The calculated 2.7% impact probability reflected this uncertainty. Not a statement that Apophis would probably hit Earth, but an acknowledgement that the observational data couldn't yet rule out such an impact. The concept of gravitational keyholes made the uncertainty even more consequential. During Apophis's close approach on April 13, 2029, Earth's gravity would deflect the asteroid's trajectory by a small but measurable amount. If Apophis passed through certain narrow regions of space during this encounter, regions only a few hundred meters wide, the gravitational deflection could set up a precise collision with Earth 7 years later, in 2036. These keyholes represent a phenomenon unique to asteroid risk assessment. A close but safe approach can evolve into an eventual collision if the geometry is precisely wrong. The keyhole for Apophis's potential 2036 impact was calculated to be roughly 610 meters wide, smaller than many city blocks, but large enough that early orbital uncertainties couldn't definitively rule out passage through it. This is where the mathematics of orbital mechanics intersected with the psychology of risk communication in problematic ways. News reports focused on the headline-grabbing 2.7% figure, while largely ignoring the underlying uncertainty that generated it. The public understandably interpreted this as a near-certain prediction, rather than a provisional calculation based on limited data. Professional astronomers knew better. They understood that additional observations would either confirm the impact threat by narrowing the uncertainty ellipse around a collision trajectory, or eliminate it by moving the most probable path away from Earth. The smart money was on the latter outcome. Most asteroid scares dissolve under the weight of additional data. But the only way to know for certain was to keep observing. The solution required a coordinated global effort, unlike anything previously attempted for a single asteroid. Observatories on every continent began tracking Apophis whenever it was visible, accumulating the measurements needed to shrink orbital uncertainties. Radio telescopes conducted radar observations that could determine distances to meter-level precision. Space-based observatories contributed astrometric measurements, free from atmospheric distortion. The breakthrough came from an unexpected source. Don Yeomans and his team realized they could extend Apophis's observational arc by mining archival sky survey images for pre-discovery detections. By searching through databases of astronomical images taken before the asteroid's formal discovery, they found additional observations dating back to March 2004, effectively doubling the time baseline available for orbital calculations. These observational arc and hundreds of additional position measurements The orbital uncertainty shrank dramatically. By late 2005, refined calculations had reduced the 2029 impact probability to effectively 0. Apophis would indeed make an extremely close approach, closer than any asteroid of comparable size in recorded history. But it would miss Earth by approximately 32,000 kilometers. The elimination of the 2029 impact didn't immediately resolve all concerns about Apophis. The asteroid would still pass close enough to the 2036 keyhole that residual uncertainties prevented a confident all-clear assessment. For several more years, Apophis retained a small but non-zero probability for later impacts, though much lower than the original calculation. Final resolution required detecting and measuring the Yarkovsky effect, the subtle orbital drift caused when an asteroid absorbs sunlight and re-radiates it as heat. This tiny but persistent force can gradually alter asteroid orbits over thousands of years, and accounting for it precisely requires extraordinary measurement precision accumulated over long time periods. The detection came in 2021, when independent teams confirmed that Apophis was drifting away from a purely gravitational orbit at a rate of -70 meters per year in semi-major axis. This measured drift was sufficient to rule out passage through the 2036 keyhole and eliminate impact risks for over a century. NASA analysis confirms Earth is safe from asteroid Apophis for 100+ years. A statement that represents one of the most thoroughly validated negative predictions in the history of planetary science. The progression from 2.7% impact probability to confident safety assessment illustrates exactly how planetary defense should work when confronted with apparent threats. The Apophis case study established protocols that now guide asteroid risk assessment and communication. Initial calculations based on limited data should be treated as preliminary, with uncertainty bounds clearly communicated. Media reports should emphasize the provisional nature of early impact probabilities, rather than treating them as definitive predictions. Additional observations typically reduce apparent threats, but this process requires sustained effort over multiple years. The institutional response to Apophis also demonstrated the importance of international coordination in planetary defense. NASA's Planetary Defense Coordination Office, the European Space Agency's Space Situational Awareness Program, and observatories worldwide work together to accumulate the data needed for confident risk assessment. This cooperation model now serves as the template for responding to future asteroid threats. Perhaps most importantly, the Apophis scare revealed the difference between statistical uncertainty and existential danger. That initial 2.7% was not a prediction that doom was approaching. It was an admission that existing data could not yet rule out such a scenario. The difference matters enormously for public communication and policy response to future asteroid discoveries. The transformation of Apophis from potential civilization ender to harmless spectacle represents science working exactly as intended. Early, alarming calculations motivated intensive follow-up observations. Additional data eliminated the apparent threat. The process took several years and involved dozens of observatories, but it worked. But what if it had not worked? What if those additional observations had confirmed, rather than eliminated, the impact threat? The hypothetical impact of an Apophis-sized asteroid provides sobering context for understanding why planetary defense matters, and why the pretty visitor from interstellar space tells us nothing about the risks that actually keep experts awake at night. Part 8. What if an Apophis-class rock hit Earth? Let's conduct a thought experiment. Imagine that those additional observations of Apophis had gone the other way. That instead of eliminating the impact threat, they had confirmed it. What would we be facing on April 13, 2029? An asteroid 340 meters in diameter, composed primarily of silicate rock and nickel iron metal, moving at approximately 25 kilometers per second relative to Earth's surface. The kinetic energy alone would exceed 500 megatons of TNT equivalent, roughly 10 times the yield of the largest nuclear weapon ever tested, the Soviet Union's Tsar Bomba of 1961. But raw energy numbers, while staggering, do not tell the complete story of what such an impact would mean for human civilization. The effects would depend critically on where Apophis hit, land or ocean, populated or remote area, geologically stable or seismically active region. Each scenario presents different challenges and different scales of catastrophe. A land impact would create a crater approximately 4 to 5 kilometers in diameter, depending on the local geology and impact angle. The initial explosion would vaporize everything within several kilometers of ground zero, creating temperatures comparable to the surface of the sun for a brief but devastating moment. The fireball would expand to roughly 15 kilometers in diameter, igniting fires across hundreds of square kilometers and killing every living thing within that zone through thermal radiation alone. But the immediate destruction zone represents only the beginning of an Apophis impact's consequences. The blast wave would propagate outward at supersonic speeds, flattening buildings and killing most people within 50 kilometers of the impact site. Seismic waves would trigger earthquakes detectable on the opposite side of the planet. The debris cloud would darken sky, disrupting agriculture and climate patterns for months or years. An ocean impact presents different but equally sobering scenarios. Contrary to popular belief, water does not significantly cushion asteroid impacts. At cosmic velocities, water behaves more like concrete than a soft landing pad. An Apophis-sized asteroid striking the ocean would vaporize millions of tons of water instantly, creating a steam explosion visible from space and generating tsunamis that could devastate coastlines thousands of kilometers away. The scale of such tsunamis depends heavily on impact location, ocean depth, and coastal geography. A strike in the deep Pacific could generate waves 10 to 20 meters high that would reach populated coastlines with little warning. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake, killed over 230,000 people across 14 countries. An Apophis impact tsunami could be significantly larger and affect even more populous regions. For context, consider the Chelyabinsk event of February 15, 2013. That asteroid was only about 20 meters in diameter, roughly 60 times smaller than Apophis by volume. Yet, its airburst injured over 1,500 people and caused millions of dollars in property damage. The shockwave broke windows across a region larger than some European countries, demonstrating how even relatively small space rocks can cause widespread disruption when they arrive without warning. Scale up from Chelyabinsk's 20-meter impactor to Apophis's 340-meter bulk, and you are looking at a qualitatively different kind of disaster. We are not talking about broken windows and startled residents. We are talking about the potential collapse of regional civilization, mass casualty events measured in millions rather than thousands, and economic disruption that would affect the entire planet for decades. The global climate effects of an Apophis-class impact would fall short of the nuclear winter scenarios associated with much larger asteroids like the Chicxulub impactor that ended the age of dinosaurs 66 million years ago. But even a regional impact could inject enough dust and debris into the stratosphere to cool global temperatures by 1 to 2 degrees Celsius for several years, disrupting agricultural cycles and threatening food security for billions of people. Modern civilization's interconnectedness would amplify the damage far beyond the immediate impact zone. Supply chain disruptions, financial market crashes, and the collapse of regional infrastructure could trigger cascading failures across continents. The 2011 Tohoku earthquake and tsunami in Japan, despite being a localized disaster, disrupted global manufacturing and shipping for months. An Apophis impact would represent a far more severe shock to the integrated global economy. The psychological and social effects might prove as devastating as the physical destruction. Unlike natural disasters that affect specific regions, an asteroid impact carries existential implications that would reverberate through human consciousness for generations. The knowledge that our planet remains vulnerable to cosmic bombardment would fundamentally alter how humanity views its place in the universe. Emergency response planning for such scenarios reveals the limitations of current disaster preparedness infrastructure. Existing protocols are designed around hurricanes, earthquakes, and other terrestrial hazards with well-understood characteristics and predictable patterns. An asteroid impact would present unprecedented challenges in terms of scale, duration, and the variety of simultaneous effects requiring coordinated response. Evacuation planning alone illustrates the complexity. For most natural disasters, people can flee to neighboring regions and expect to return home relatively quickly. An Apophis-class impact would render large areas uninhabitable for years or decades, requiring permanent resettlement of potentially millions of people. The logistics of such massive population movements would strain governmental and humanitarian resources beyond current capabilities. International cooperation would become essential for effective response and recovery. No single nation possesses the resources to manage an Apophis-scale disaster independently. Yet the current framework for international disaster response operates on assumptions about regional events with limited global consequences. An asteroid impact would require unprecedented coordination between governments, international organizations, and relief agencies. The economic cost would dwarf any previous natural disaster. The 2011 Tohoku earthquake and tsunami caused approximately $200 billion in direct damage. Hurricane Katrina in 2005 generated over $125 billion in losses. An Apophis impact could easily generate damage costs exceeding $1 trillion, not including the longer-term economic disruption from climate effects and mass displacement. These sobering calculations illuminate why planetary defense has evolved from science fiction curiosity to serious policy priority. The low probability of any individual asteroid impact must be weighed against the catastrophic consequences if such an impact actually occurs. Risk assessment professionals call this the high-consequence, low-probability scenario. Events that are unlikely to happen in any given year, but would be devastating if they did occur. But here is the crucial point that brings us back to our original comparison between Oumuamua and Apophis. Probability matters as much as consequences. Oumuamua, despite its exotic interstellar origins and extensive media coverage, has exactly zero chance of causing the scenarios we have just described. Its trajectory takes it nowhere near Earth, and its hyperbolic orbit means it will never return to pose a future threat. Apophis, by contrast, represented a real, if ultimately unconfirmed, threat precisely because it follows an Earth-crossing orbit. Even though additional observations eliminated its impact risk for the next century, it remains a member of the potentially hazardous asteroid population. Objects whose orbits bring them close enough to matter, and whose sizes make them dangerous if they ever do hit. The distinction between spectacular and dangerous has never been clearer. Oumuamua commands attention because of its rarity and exotic origins, while Apophis offers genuine insights into the kinds of threats that planetary defense systems are designed to address. One is a beautiful curiosity. The other is a case study in why we need to take near-Earth asteroids seriously. This brings us to the heart of why Oumuamua, for all its scientific value, represents a dangerous distraction from the real work of planetary defense. While we are marveling at the harmless visitor from interstellar space, the threats that actually matter are quietly following their elliptical orbits, occasionally passing uncomfortably close to the only planet we have got. Part 9. Why Oumuamua is harmless but Apophis remains wake-up call. Sometimes the most important lesson comes not from what threatens us, but from what does not. Oumuamua and Apophis represent perfect opposites in the taxonomy of space hazards. One spectacular and safe, the other ordinary and genuinely concerning. Understanding why this matters requires looking beyond the headlines to the underlying mathematics of orbital mechanics and risk assessment. Let's start with the numbers that actually matter. Oumuamua will reach its closest approach to Earth on December 19, 2025, at a distance of approximately 1.79.7 astronomical units. That's roughly 268 million kilometers, a gap so vast that the Moon could fit in that space nearly 700 times over. At no point in its hyperbolic trajectory does Oumuamua come anywhere close to Earth's orbital neighborhood. Apophis, by contrast, will pass just 32,000 kilometers from Earth's surface on April 13, 2029. To put that in perspective, our geostationary communications satellites orbit at 35,786 kilometers altitude. Apophis will literally thread the needle between Earth and critical space infrastructure, passing closer to our planet than objects we have deliberately placed in orbit. The distance comparison reveals everything you need to know about the difference between media-worthy and genuinely significant space encounters. Oumuamua misses Earth by a factor of more than 8,000 compared to Apophis's closest approach. Yet, which object has dominated headlines and captured public imagination? The answer lies in a fundamental misunderstanding of how danger scales with rarity. Oumuamua earns attention precisely because it's exotic. Only the third confirmed interstellar object ever detected passing through our solar system. The visitor from another star narrative writes itself, complete with speculation about alien origins and mysterious compositions. Our brains are wired to find the unusual more compelling than the routine, even when routine events pose greater actual risks. Apophis follows a perfectly ordinary near-Earth asteroid orbit. It's composed of common silicate rock and nickel-iron metal materials found throughout the inner solar system. Its discovery required no revolutionary observational techniques, just the patient, systematic sky surveys that detect thousands of similar objects every year. By every measure, except the one that actually matters, proximity to Earth, Apophis is utterly unremarkable. Yet, Apophis briefly held the record for highest calculated impact probability of any known asteroid. Its early threat assessment reached level 4 on the Torino scale, unprecedented for a real object with a specific predicted impact date. The initial 2.7% probability of collision in 2029 represented a genuine crisis in planetary defense, mobilizing observatories worldwide and forcing the development of new protocols for asteroid risk communication. The institutional response to Apophis revealed how seriously space agencies take near-Earth asteroid threats when they appear credible. NASA's Planetary Defense Coordination Office did not exist when Apophis was discovered in 2004. But the crisis it generated helped justify the office's creation. The European Space Agency expanded its Space Situational Awareness program, partly in response to lessons learned from the Apophis scare. No comparable institutional response has emerged around Oumuamua, nor should it. The interstellar comet poses no threat, requires no special monitoring beyond normal scientific observation, and offers no lessons applicable to planetary defense scenarios. It's fascinating, but irrelevant to the practical work of protecting Earth from cosmic impacts. This brings us to the heart of why Oumuamua represents both an opportunity and a danger for public education about space hazards. The opportunity lies in using its spectacular nature to capture attention, and then redirecting that attention toward objects that actually matter. The danger lies in allowing exotic but harmless visitors to overshadow the mundane but genuine threats that share our cosmic neighborhood. Consider the typical life cycle of an Oumuamua news story. It begins with breathless announcements about the alien visitor approaching our solar system. Early reports emphasize the rarity and mystery of interstellar objects, often with dramatic images of the comet's growing tail and expanding coma. The safety disclaimers appear later, buried in technical details that most readers skip. Near-Earth asteroid discoveries rarely make headlines, unless they are associated with immediate impact threats. The steady accumulation of knowledge about potentially hazardous asteroids happens in specialized journals and technical databases that the public never sees. We have cataloged over 34,000 near-Earth asteroids, but most people could not name 5 of them besides Apophis. This asymmetry in coverage creates a distorted perception of space hazards. The public becomes familiar with harmless but spectacular visitors, while remaining largely ignorant of the genuine threats that planetary defense systems are designed to address. When the next Apophis-class object is discovered, and statistical analysis suggests there are many more waiting to be found, public confusion about relative risks could complicate policy responses and resource allocation decisions. The difference extends beyond mere publicity to fundamental questions about how we assess and communicate risks in an era of information overload. 3IATLAS generates thousands of news articles, social media posts, and amateur astronomy discussions, despite posing zero threat to Earth. Meanwhile, the patient work of cataloging potentially hazardous asteroids continues largely unnoticed. Even though this work provides our only realistic defense against future impact threats, NASA's clear communication about 3IATLAS's safety demonstrates how space agencies have learned from the Apophis experience. Every official statement about the interstellar comet emphasizes its harmless trajectory and vast distance from Earth. These are not euphemisms or attempts to avoid panic. They are mathematical certainties based on orbital mechanics that leave no room for interpretation. The same clarity applied to Apophis in reverse. Official statements now confirm that Earth is safe from this asteroid for at least 100 years. Based on precise measurements that eliminated earlier concerns about potential impacts, the progression from uncertainty to confidence illustrates how planetary defense is supposed to work when confronted with apparent threats. But the broader lesson extends beyond individual objects to systematic approaches to space hazard assessment. 3IATLAS represents the category of threats we do not need to worry about. Rare visitors on hyperbolic trajectories that will never return. Apophis represents the category we do need to monitor continuously. Near-Earth asteroids, whose orbits evolve over time and occasionally bring them uncomfortably close to home. The distinction matters for resource allocation and policy priorities. Every dollar spent studying harmless interstellar visitors is a dollar not available for the unglamorous but essential work of near-Earth asteroid surveys. Every hour of telescope time devoted to exotic comets is an hour not spent tracking potentially hazardous asteroids that might pose future threats. This is not an argument against studying 3IATLAS or other interstellar objects. They provide valuable scientific insights about planetary formation and the distribution of materials throughout the galaxy. But it is an argument for maintaining perspective about which discoveries matter for human survival and which represent purely scientific curiosities. The 2029 encounter with Apophis offers a perfect counterpoint to 3IATLAS's harmless spectacle. While the interstellar comet will disappear forever into the void between stars, Apophis will provide an unprecedented opportunity to study a potentially hazardous asteroid under controlled conditions. The data collected during its close approach will inform planetary defense strategies for decades to come. That data collection represents the real work of planetary defense. Patient accumulation of knowledge about near-Earth asteroids, development of deflection technologies, and preparation for the day when we might face a genuine impact threat. It is not as photogenic as an interstellar visitor trailing a glowing tail, but it is infinitely more important for long-term human survival. The contrast between 3IATLAS and Apophis illuminates a fundamental truth about risk assessment. Danger is not determined by rarity or spectacle, but by proximity, combined with probability. The exotic visitor poses no threat despite commanding headlines. The ordinary neighbor remains a subject of legitimate scientific interest, despite being declared safe for the next century. Part 10. The 2029 show, What We Will Measure, April 13, 2029, will mark the most intensively observed asteroid encounter in human history. Every major observatory on Earth will be watching Apophis during its closest approach. Armed with instruments that can measure changes in the asteroid's properties down to unprecedented levels of detail. The global observation campaign represents a coordination effort unlike anything attempted for a single astronomical object. Ground-based optical telescopes will track changes in Apophis's brightness and color that might indicate surface modifications triggered by tidal stress. Infrared observatories will map temperature variations across the asteroid's surface, looking for thermal signatures of freshly exposed subsurface material. Radio telescopes will conduct high-resolution radar imaging to document any structural changes with meter-level precision. The timing provides a natural before and after comparison that planetary scientists have been planning for years. Detailed observations of Apophis, conducted during its 2021 apparition, established a baseline data set of the asteroid's properties, its shape, rotation rate, surface composition, and thermal characteristics. The 2029 encounter will allow researchers to measure exactly how Earth's gravitational influence modified these parameters. Radar observations will play a crucial role in this comparison. The Goldstone Solar System radar in California and the Green Bank Radio Telescope in West Virginia can achieve spatial resolutions of just a few meters when observing Apophis during its close approach. These facilities documented the asteroid's shape in exquisite detail during previous encounters, creating three-dimensional models that show individual boulders and surface features. If tidal forces do trigger significant changes during the flyby, landslides among loose surface material, the exposure of fresh subsurface rock, or alterations to the distribution of boulders and debris, radar observations should detect them immediately. The comparison between pre-encounter and post-encounter radar images could provide the first direct evidence of how asteroids respond to strong gravitational perturbations. The asteroid's rotation presents another critical measurement target. Apophis currently rotates once every 30.6 hours, a leisurely tumble that carries different faces into sunlight on a predictable schedule. Earth's gravity will almost certainly alter this rotation rate, either spinning the asteroid up or slowing it down depending on complex interactions between tidal forces and the asteroid's elongated shape. Measuring these changes requires extraordinary precision in photometric observations. Monitoring how Apophis varies as different parts of its surface rotate into view, professional observatories worldwide will contribute data to this effort. But amateur astronomers will also play a crucial role. The International Astronomical Union has been coordinating amateur observation campaigns for years, and the 2029 encounter represents the ultimate test of citizen science capabilities. The thermal infrared observations deserve special attention because they could reveal the most dramatic changes triggered by the encounter. Space weathering, the gradual darkening and reddening of asteroid surfaces caused by micrometeorite bombardment and solar wind exposure, occurs over millions of years under normal circumstances. If tidal stress exposes large amounts of fresh subsurface material, that material should appear brighter and less red than the space-weathered surface layers. NASA's NEOWISE mission has been conducting thermal infrared surveys of near-Earth asteroids since 2013, providing baseline measurements of surface temperatures and thermal properties for thousands of objects, including Apophis. The 2029 observations will determine whether the encounter altered these thermal characteristics in measurable ways. Spectroscopic observations will attempt to detect compositional changes that might result from surface modifications. Different minerals reflect and absorb light at characteristic wavelengths, creating spectral fingerprints that reveal asteroid composition. If significant amounts of fresh material are exposed during the encounter, spectrographs should detect differences in the relative abundances of various mineral components. The European Space Agency's Hera mission, launched in October 2024, will be operating in the vicinity of the Didymos asteroid system during Apophis's encounter with Earth. While Hera will not observe Apophis directly, its advanced instruments and operational experience with asteroid characterization will inform data analysis and interpretation for the encounter observations. Perhaps most intriguingly, the 2029 encounter will provide the first opportunity to study how an asteroid's internal structure responds to external stress. Most asteroids are thought to be rubble piles, loose collections of boulders, rocks, and debris held together by weak gravitational attraction rather than material strength. But the degree of internal coherence varies significantly between different asteroids, and this variation has important implications for planetary defense applications. If Apophis proves to be a relatively coherent object with significant internal strength, tidal forces might produce only minor surface changes. If it is a loose rubble pile barely held together by gravity, the encounter could trigger more dramatic restructuring. The observations will provide crucial ground truth for models used to predict how asteroids respond to deflection attempts. The asteroid's elongated shape adds complexity to these predictions. Tidal forces do not affect spherical objects uniformly. They stretch objects along the line connecting them to the perturbing body, while compressing them perpendicular to that line. For an elongated asteroid like Apophis, the orientation during closest approach will determine whether tidal stress acts to further elongate the object or to make it more spherical. Current models suggest that Apophis will experience maximum tidal stress at 21 hours, 46 minutes universal time, on April 13th, when it passes closest to Earth. At that moment, Earth's gravitational field will exert forces on the asteroid roughly 50 times stronger than its own self-gravity. For comparison, the tidal forces that Earth experiences from the Moon are about 10 million times weaker relative to Earth's self-gravity. The coordinated observation campaign will test the limits of ground-based astronomical capabilities. Multiple observatories on different continents will need to hand off observations as Earth's rotation carries Apophis across the sky. Real-time data sharing will allow researchers to adjust observing strategies based on preliminary results from earlier phases of the encounter. Communication delays add urgency to the observation planning. Light takes approximately 0.1 seconds to travel from Apophis to Earth during closest approach. Fast enough for real-time observations, but slow enough that rapid changes in the asteroid's behavior could be missed if observers are not prepared. Pre-planned observation sequences will ensure comprehensive coverage, even if unexpected events occur during the encounter. The data collected during the 2029 encounter will influence asteroid science and planetary defense research for decades. Current computer models of asteroid structure and behavior rely heavily on theoretical assumptions about material properties, internal cohesion, and mechanical response to external forces. Apophis will provide the first opportunity to validate these models against direct observations of an asteroid undergoing measurable stress. The implications extend beyond pure science to practical questions about planetary defense strategies. Understanding how asteroids respond to tidal stress informs predictions about how they might react to kinetic impact missions or other deflection techniques. If Apophis proves more or less coherent than expected, those findings could influence the design of future planetary defense missions. But perhaps the most important aspect of the 2029 observation campaign is its role as a dress rehearsal for genuine planetary defense scenarios. The international coordination, real-time data sharing, and comprehensive measurement techniques being developed for Apophis could prove essential if we ever face an actual impact threat requiring immediate characterization and response. Unlike 3IATLAS, which offers no practical lessons for planetary defense, the Apophis encounter will generate actionable knowledge that could someday help protect our planet from genuine cosmic threats. Part 11. From Scare to Strategy, Planetary Defense Tactics. The transformation of Apophis from existential threat to scientific opportunity represents more than just improved orbital calculations. It marks the evolution of planetary defense from reactive panic to proactive strategy. When Apophis was discovered in 2004, no formal planetary defense infrastructure existed. NASA had various programs for detecting and tracking near-Earth asteroids, but no coordinated office responsible for impact hazard assessment and mitigation planning. The European Space Agency conducted asteroid research, but had no dedicated planetary defense mandate. The international community possessed no formal mechanisms for coordinating responses to potential impact threats. The Apophis scare changed everything. By 2006, NASA had established the Near-Earth Object Observations Program, with dedicated funding for asteroid surveys and follow-up observations. The program's mandate explicitly included both discovery of potentially hazardous asteroids and precise characterization of their orbits to assess impact risks. This represented the first institutional recognition that planetary defense required sustained, systematic effort, rather than ad hoc responses to individual threats. The European Space Agency followed suit with its Space Situational Awareness Program, later renamed Space Safety and Security. Initially focused on space debris and solar weather hazards, the program expanded to include near-Earth asteroid detection and risk assessment. The ESA's collaboration with ground-based observatories and space surveillance networks created Europe's first comprehensive approach to planetary defense. But institutional frameworks alone could not address the technical challenges revealed by the Apophis case. Deflecting a threatening asteroid requires precise knowledge of its physical properties: mass, density, internal structure, surface composition, and mechanical strength. These parameters determine how an asteroid responds to deflection attempts and influence the design of mitigation missions. The Double Asteroid Redirection Test, launched in November 2021, represented humanity's first practical experiment in asteroid deflection technology. DART's target was Dimorphos, the smaller member of a binary asteroid system orbiting the larger asteroid Didymos. The mission's objective was straightforward: crash a spacecraft into Dimorphos at high speed and measure the resulting change in its orbital period around Didymos. DART succeeded beyond expectations. The impact on September 26, 2022, changed Dimorphos's orbital period by 32 minutes, more than 3 times the minimum 10-minute change needed to declare the mission successful. The momentum enhancement factor beta, which measures how efficiently impact momentum translates into orbital change, reached approximately 3.6, indicating that debris ejected from the impact site provided additional thrust beyond the spacecraft's direct momentum transfer. This momentum multiplication effect had been predicted by computer models, but never demonstrated in practice. The DART impact validated theoretical predictions about how loose rubble pile asteroids respond to kinetic impacts, providing crucial calibration data for future deflection missions. The success proved that kinetic impactor technology could reliably alter asteroid trajectories, given sufficient advanced warning and careful mission design. The European Space Agency's Hera mission, launched in October 2024, will arrive at the Didymos system in late 2026 to conduct detailed post-impact analysis. Hera's instruments will measure the precise crater size and shape created by DART's impact, map changes in Dimorphos's surface properties, and determine how the impact affected the asteroid's internal structure and rotation state. The DART-HERA collaboration establishes the template for future planetary defense missions. The kinetic impactor demonstrates deflection capability, while the follow-up reconnaissance mission provides the detailed measurements needed to validate computer models and plan future operations. This two-phase approach ensures that theoretical predictions about asteroid deflection are grounded in empirical data from actual space operations. The success of DART has direct implications for Apophis and other potentially hazardous asteroids. The momentum transfer techniques validated at Dimorphos could be applied to deflect genuine threats given sufficient warning time. More importantly, the mission demonstrated international cooperation in planetary defense. DART was a NASA mission, with significant contributions from European partners and coordination with observatories worldwide. The institutional infrastructure surrounding planetary defense has continued to mature since the DART impact. NASA's Planetary Defense Coordination Office, established in 2016, now coordinates all agency activities related to planetary defense, including asteroid detection, characterization, and mitigation planning. The office maintains close relationships with international partners and serves as the United States government's focal point for planetary defense policy. The International Asteroid Warning Network, established by the United Nations Committee on the Peaceful Uses of Outer Space, provides a forum for sharing information about asteroid discoveries and potential threats. IAWN coordinates observations of newly discovered objects, facilitates rapid communication about impact hazards, and serves as an authoritative source for asteroid threat assessments. The Space Mission Planning Advisory Group, also established under UNCOPUOS, focuses on the technical aspects of deflection missions. SMPAG develops guidelines for planetary defense missions, coordinates international planning for potential deflection operations, and serves as a bridge between the scientific community and national space agencies. These institutional developments reflect hard-earned lessons from the Apophis experience about the importance of clear communication channels, authoritative risk assessment, and coordinated international response to potential threats. The chaotic early years of Apophis observations, when different groups produced conflicting impact probability estimates, demonstrated the need for standardized procedures and designated authorities. The technological capabilities supporting planetary defense have expanded dramatically since 2004. The linear and neat asteroid surveys that dominated near-Earth object discovery in the early 2000s have been supplemented by more capable systems like the Asteroid Terrestrial Impact Last Alert System and the Zwicky Transient Facility. These ground-based surveys discover thousands of new near-Earth asteroids annually while conducting follow-up observations of previously known objects. The upcoming NEO Surveyor mission represents the next major advancement in asteroid detection capabilities. This space-based infrared telescope, scheduled for launch no earlier than late 2027, will be optimized for discovering dark, hard-to-detect asteroids that are invisible to ground-based optical surveys. NEO Surveyor should dramatically accelerate the discovery rate for potentially hazardous asteroids in the 100 to 500 meter size range. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in 2025 and conduct the legacy survey of space and time. LSST's unprecedented combination of wide field of view, rapid cadence, and deep sensitivity will revolutionize near-Earth asteroid science, potentially discovering hundreds of thousands of new objects while providing precise orbit determinations for known asteroids. But perhaps the most important development in planetary defense has been the recognition that the problem extends beyond purely technical challenges to include policy, legal, and social dimensions. Deflecting an asteroid requires not just the right technology, but also the authority to act, the resources to fund missions, and the international cooperation to coordinate responses. The Apophis case study revealed how quickly an apparent asteroid threat can escalate from scientific curiosity to public concern to policy crisis. The initial 2.7% impact probability generated congressional hearings, emergency funding requests, and international diplomatic discussions about responsibilities for planetary defense. While additional observations eliminated the specific threat, the experience highlighted the need for pre-established decision-making frameworks and response protocols. Current planetary defense planning assumes that genuine impact threats will be detected years or decades before potential collision, providing sufficient time for careful mission design and international coordination. The DART mission validated deflection technology for this scenario, demonstrating that kinetic impactors can reliably change asteroid orbits given adequate preparation time. But the smaller asteroids that make up the majority of undiscovered near-Earth objects might not provide such generous warning times. Objects in the 10 to 100 meter size range could potentially arrive with only months or years of advanced warning, requiring rapid response deflection capabilities that don't currently exist. The planetary defense community has begun addressing this challenge through studies of fast response mission architectures and pre-positioned deflection systems. These concepts remain largely theoretical, but they represent the kind of forward-thinking approach that emerged from lessons learned during the Apophis scare. The evolution from Apophis crisis to DART success illustrates how scientific understanding and technological capability can mature rapidly when properly motivated. The same institutional frameworks and technical capabilities that eliminated the Apophis threat now stand ready to address genuine impact hazards that might be discovered in the future. This infrastructure represents humanity's insurance policy against cosmic catastrophe, an investment in capabilities we hope never to use, but can't afford to lack when the time comes. Part 12. Cataloging the threats we actually face. While 3IATLAS captures headlines with its exotic interstellar origins, the real work of planetary defense happens in the methodical cataloging of ordinary near-Earth asteroids, following predictable orbits through our cosmic neighborhood. The taxonomy of near-Earth objects reveals why some asteroids matter more than others for planetary defense purposes. The Aten group orbits primarily inside Earth's path around the Sun, with semi-major axes less than 1 astronomical unit, but aphelion distances that carry them beyond 0.983 AU. These asteroids spend most of their time closer to the Sun than Earth, but their elliptical orbits still bring them across our planet's trajectory at regular intervals. The Apollo group follows orbits that directly cross Earth's path with semi-major axes greater than 1 astronomical unit, but perihelion distances less than 1.017 AU. This group contains some of the most potentially dangerous asteroids because their orbits intersect Earth's trajectory twice per revolution, maximizing opportunities for close encounters. Apophis belongs to this category, as do most of the asteroids that have generated genuine impact scares over the past 2 decades. The Amor group approaches from outside Earth's orbit, with perihelion distances between 1.017 and 1.3 astronomical units. These asteroids don't currently cross Earth's orbital path, but gravitational perturbations over time can evolve their orbits inward until they become Earth crossers. The Amor asteroids represent the future threat population, objects that are safe today, but could become dangerous as their orbits evolve. Finally, the Atira group orbits entirely inside Earth's path, though some members can still approach our planet during their most distant excursions from the Sun. These asteroids are particularly difficult to discover because they're always located in the same general direction as the Sun from Earth's perspective, limiting observing opportunities to brief periods during twilight. Within these orbital families, planetary defense experts focus on potentially hazardous asteroids, PHAS, defined by size and proximity criteria that translate to genuine impact risk. A PHA must have a minimum orbital intersection distance with Earth of less than 0.05 astronomical units, approximately 7.5 million kilometers, and an absolute magnitude brighter than 22, corresponding to a diameter of roughly 140 meters or larger. That size threshold reflects a careful balance between impact frequency and consequences. Smaller asteroids hit Earth more often, but cause only localized damage. Larger asteroids cause more widespread devastation, but arrive much less frequently. The 140-meter threshold captures objects large enough to devastate major metropolitan areas, while small enough that many remain undiscovered in existing surveys. Current catalogs contain over 2,000 confirmed PHAs, with new discoveries added at a rate of several hundred per year as ground-based surveys improve their detection capabilities. But these numbers represent only a fraction of the total population. Statistical analysis suggests that tens of thousands of PHAs remain undiscovered, hidden in the glare of the Sun, or too dark to detect with current optical surveys. The discovery statistics tell a story of accelerating awareness. In 1990, astronomers knew of fewer than 200 near-Earth asteroids of all sizes. By 2000, systematic surveys had increased that number to over 1,000. Today, the catalog contains more than 34,000 confirmed NEAs, with roughly 3,000 new discoveries each year. The larger objects, those capable of causing global catastrophes, are mostly accounted for. Ground-based surveys have discovered an estimated 90% or more of near-Earth asteroids larger than 1 kilometer in diameter. None of these kilometer-class objects pose any near-term impact threat, providing reassurance about extinction-level events for at least the next several centuries. But the smaller objects that could cause regional disasters remain largely undiscovered. Current estimates suggest that fewer than 40% of the 140-meter class PHAs have been found. The discovery rate for these objects is limited by the sensitivity of ground-based optical telescopes, which can only detect relatively bright asteroids against the background glow of the night sky. This detection bias creates a dangerous gap in our knowledge. The asteroids we're missing aren't exotic interstellar visitors or unusual compositional types. They're ordinary near-Earth asteroids that happen to be dark, small, or poorly positioned for ground-based observation. These mundane objects could arrive with little warning and cause catastrophic damage if they struck populated areas. The Chelyabinsk meteor of February 15, 2013, illustrates this detection problem perfectly. The incoming asteroid was only about 20 meters in diameter, well below the PHA size threshold. But it still managed to injure over 1,500 people and cause millions of dollars in property damage. The object approached from the direction of the Sun, making pre-impact detection nearly impossible with ground-based telescopes. Scale up from Chelyabinsk's 20-meter impactor to a 140-meter PHA, and you're looking at a potential regional catastrophe affecting millions of people. Yet many such objects remain undiscovered, simply because they're too dark or too small for current surveys to detect reliably. The solution lies in space-based infrared observations that can detect asteroid thermal emission regardless of surface reflectivity. The upcoming NEO Surveyor mission represents a major advancement in this direction. A dedicated asteroid hunting telescope, optimized for discovering dark objects that are invisible to ground-based optical surveys. NEO Surveyor will observe in thermal infrared wavelengths where asteroids glow due to solar heating rather than reflected sunlight. This approach eliminates the detection bias that favors bright reflective objects while missing dark ones of similar size. The mission should dramatically accelerate discovery rates for potentially hazardous asteroids in the size range that poses the greatest undiscovered threat. The technological capabilities supporting these surveys have improved dramatically over the past 2 decades. The linear survey, which dominated near-Earth object discovery in the late 1990s and early 2000s, used relatively modest 1-meter telescopes with basic CCD cameras. Today's surveys employ larger telescopes, more sensitive detectors, and sophisticated software for automated detection and follow-up of moving objects. The Asteroid Terrestrial Impact Last Alert System operates telescopes in Hawaii, South Africa, Chile, and Australia, providing nearly continuous coverage of the entire accessible sky. ATLAS can detect asteroids as small as 20 meters in diameter, just days before potential Earth impact, offering at least minimal warning for Chelyabinsk-class events. The Zwicky Transient Facility conducts rapid wide-area surveys, using a state-of-the-art camera with over 500 megapixels of detection area. ZTF discovers thousands of asteroids annually, while also conducting follow-up observations to refine orbits and assess impact risks for newly discovered objects. The upcoming Vera C. Rubin Observatory will dwarf all previous survey capabilities when it begins operations in 2025. The Legacy Survey of Space and Time will image the entire accessible sky twice per week, potentially discovering hundreds of thousands of new asteroids, while providing precise orbit determinations that eliminate most sources of uncertainty in impact risk assessment. But discovery represents only the first step in the planetary defense process. Each newly detected asteroid requires follow-up observations to determine its orbit precisely enough for reliable impact hazard assessment. This follow-up process can take months or years, during which impact probabilities remain uncertain and potentially alarming. The Apophis experience taught planetary defense experts that early impact probability calculations, based on limited observational data, should be treated with extreme caution. Most asteroid scares dissolve as additional observations shrink orbital uncertainties and move predicted trajectories away from Earth impact. But this process requires sustained observational effort and clear communication about the difference between preliminary calculations and confident predictions. NASA's Center for Near-Earth Object Studies maintains the authoritative database of asteroid orbits and impact risk assessments. Their Sentry system automatically scans the orbits of all known near-Earth asteroids, searching for potential future impacts and calculating associated probabilities. Objects with non-trivial impact probabilities are flagged for additional observations to reduce uncertainties. The systematic approach to asteroid threat assessment developed over the past 2 decades represents a triumph of applied astronomy. The same techniques that eliminated the Apophis impact threat now operate continuously, screening thousands of asteroid orbits for potential future hazards and triggering follow-up observations when needed. This infrastructure provides humanity's early warning system for cosmic catastrophe, an automated sentinel that never sleeps, never stops searching, and stands ready to detect the next potential threat years or decades before it arrives. Part 13. Communicating Risk Without Fear. April 13, 2029, will present an unprecedented opportunity and challenge for science communication. How do you explain that an asteroid passing closer than our satellites is completely safe, while maintaining public trust in scientific institutions. The naked-eye visibility of Apophis during its close approach represents a double-edged sword for planetary defense education. Weather permitting, observers across Europe, Africa, and Western Asia will be able to see the asteroid as a moving point of light crossing the night sky. Without telescopes or special equipment, this visibility offers an extraordinary chance to engage the public with asteroid science. But it also risks generating anxiety about an object that poses no threat. The communication challenge stems from a fundamental disconnect between proximity and danger. In this specific case, Apophis will pass closer to Earth than any asteroid of comparable size in recorded history, close enough to thread between our planet and the geostationary satellite belt. Yet, it represents zero impact risk for at least the next century. Explaining this apparent contradiction requires careful attention to both scientific accuracy and public psychology. The key message must remain absolutely clear and consistent across all official communications. Apophis poses no threat to Earth during its 2029 flyby, or for at least 100 years afterward. This statement isn't hedged with uncertainties or qualified with technical caveats. It represents a mathematical certainty based on precise orbital calculations, validated by decades of observations. NASA's approach to Apophis communication has evolved significantly since the early years of uncertainty following its discovery. Current public statements emphasize the safety assessment up front, followed by scientific details about the encounter's importance for asteroid research. This represents a deliberate reversal from early communication strategies that buried safety assurances in technical language, while leading with dramatic proximity statistics. The European Space Agency has adopted similar communication protocols, consistently emphasizing that Apophis will safely fly by Earth while describing the scientific opportunities presented by such a close encounter. These organizations learned from the Apophis scare of the mid-2000s that clear, unambiguous safety messages must precede technical discussions of orbital mechanics and scientific objectives. Visual aids will play a crucial role in public education campaigns surrounding the encounter. Accurate scale diagrams showing Earth, the Moon's orbit, geostationary satellite altitude, and Apophis's trajectory help audiences understand both the proximity and safety of the flyby. These graphics must avoid sensationalism while conveying the genuine significance of such a close approach by a large asteroid. The timing presents both opportunities and challenges for global coordination of public messaging. The encounter occurs during April, when many astronomical societies hold public outreach events, and when weather conditions are favorable for evening observations in the Northern Hemisphere. However, the asteroid will be visible primarily from the Eastern Hemisphere, requiring international cooperation to maximize public engagement opportunities. Amateur astronomy communities worldwide are already planning coordinated observation campaigns for the Apophis encounter. These grassroots efforts provide valuable opportunities for public education while contributing meaningful scientific data to professional researchers. The International Astronomical Union has been working with amateur astronomy organizations to develop standardized observation protocols and data sharing procedures. The social media landscape presents particular challenges for accurate risk communication about Apophis. The proximity statistics passing closer than geostationary satellites provide irresistible material for sensationalized headlines and viral misinformation. Planetary defense experts must be prepared to counter false narratives while maintaining scientific credibility and public trust. Preemptive education campaigns can help inoculate the public against common misconceptions about the encounter. Many people will assume that such a close approach must pose some risk of collision with satellites or unexpected trajectory changes. explaining the precise orbital mechanics that govern the flyby and why these calculations are absolutely reliable, requires translating complex mathematics into accessible language. The contrast with Oumuamua offers a valuable teaching opportunity. While the interstellar object generates headlines about alien visitors, despite posing zero threat, Apophis represents a genuine member of the potentially hazardous asteroid population that happens to be safe for this particular encounter. This distinction illuminates the difference between media-worthy, scientifically significant space encounters. Educational institutions are developing curriculum materials around the Apophis flyby that emphasize both the safety of this specific event and the broader importance of planetary defense research. These materials can help students understand concepts like orbital mechanics, gravitational perturbations, and statistical risk assessment using a visible, tangible example. The encounter also provides an opportunity to explain how planetary defense actually works in practice. The transformation of Apophis from potential threat to confirmed safety case illustrates the scientific process of hypothesis testing, uncertainty reduction, and evidence-based conclusion. This process represents science working exactly as intended. Despite early media coverage that focused on alarm rather than methodology, public engagement events surrounding the flyby should emphasize the positive aspects of planetary defense research. The same observational and analytical capabilities that confirmed Apophis's safety continue to operate continuously, searching for and characterizing potential future threats. The infrastructure developed to study Apophis now protects humanity from genuine impact hazards that might be discovered in the future. The international cooperation demonstrated by Apophis research provides another positive message for public consumption. Observatories on every continent have contributed data to refine the asteroid's orbit and confirm its safety. This collaboration transcends political boundaries and demonstrates how shared scientific challenges can unite the global community. Professional astronomy organizations are coordinating messaging to ensure consistency across different countries and languages. The International Astronomical Union's Commission A1 on Astrometry maintains guidelines for asteroid risk communication that emphasize clarity, accuracy, and appropriate context for public audiences. These guidelines helped standardize the language used to describe Apophis's safety status. The role of authoritative sources becomes crucial during periods of heightened public attention. NASA's Planetary Defense Coordination Office, the European Space Agency's Space Safety and Security Program, and the International Asteroid Warning Network represent the official sources for asteroid threat assessments. Public communication strategies must direct audiences to these authoritative sources while countering misinformation from less reliable outlets. Media training for scientists involved in Apophis research emphasizes the importance of leading with safety messages while avoiding technical jargon that might obscure the main point. Researchers are coached to begin interviews with clear statements about the lack of impact risk before discussing the scientific significance of the encounter. The encounter provides an opportunity to highlight the success of planetary defense investments over the past 2 decades. The observational capabilities and analytical tools that transformed Apophis from threat to opportunity represent sustained public investment in scientific infrastructure that protects civilization from cosmic catastrophe. Public opinion polling conducted during previous asteroid encounters suggests that clear, consistent messaging from authoritative sources effectively maintains public confidence in scientific institutions. The key is avoiding mixed messages or unnecessary technical complexity that might generate confusion or skepticism about official safety assessments. The Apophis encounter also provides a platform for discussing the broader context of space hazards and humanity's place in the cosmic environment. While this specific asteroid poses no threat, the existence of potentially hazardous asteroids in general represents a genuine, long-term challenge that requires sustained attention and resources. The educational value of the encounter extends beyond astronomy to broader lessons about risk assessment, scientific methodology, and evidence-based decision-making. These skills prove valuable in many contexts beyond asteroid science. From evaluating medical treatments to understanding climate change, to assessing technological risks, the success of Apophis communication efforts will be measured not just by public understanding of this specific encounter, but by lasting improvements in scientific literacy and trust in evidence-based institutions. The goal is creating an informed public that can distinguish between legitimate scientific concerns and sensationalized media narratives. As April 13, 2029 approaches, the planetary defense community faces its biggest test in science communication since the original Apophis scare 25 years earlier. This time, they're prepared with clear messages, consistent protocols, and 2 decades of experience in explaining why proximity doesn't always equal danger. Part 14. What comes after 2029? The story of Apophis doesn't end with its spectacular flyby on April 13, 2029. In many ways, that encounter marks the beginning of the most scientifically valuable phase of humanity's relationship with this remarkable asteroid. The immediate aftermath of the close approach will provide unprecedented data about how asteroids respond to strong gravitational perturbations. Ground-based observers worldwide will continue tracking Apophis for months after the encounter, measuring its new orbit and rotation state with extraordinary precision. These observations will reveal exactly how Earth's gravity modified the asteroid's trajectory and spin, providing crucial validation for computer models used in planetary defense planning. The orbital changes will be permanent and measurable. Earth's gravity will alter Apophis's semi-major axis, eccentricity likely change the asteroid's rotation period and pole orientation. These modifications represent a natural experiment in celestial mechanics that astronomers have never had the opportunity to study before. Osiris Apex will arrive at Apophis approximately 2 months after the Earth encounter, beginning an 18-month detailed study of the post-flyby asteroid. The spacecraft will document any surface changes triggered by tidal stress, measure the altered gravitational field, and conduct the ambitious thruster disturbance experiment to expose subsurface materials for remote analysis. The scientific data collected by OSIRIS-APEX will have direct applications to future planetary defense missions. Understanding how Apophis's surface and internal structure responded to Earth's gravitational influence will inform predictions about how similar asteroids might react to kinetic impactor deflection attempts. This knowledge could prove crucial for designing effective mitigation missions against genuine threats. The lessons learned from Apophis will likely influence the next generation of planetary defense technologies. Current deflection concepts rely heavily on theoretical models of asteroid structure and behavior. The empirical data from Apophis's encounter with Earth will provide ground truth for these models, potentially revealing that our assumptions about asteroid mechanics are either more or less accurate than expected. If Apophis proves more coherent than typical rubble pile models predict, future deflection missions might need to deliver more energy to achieve desired trajectory changes. If it proves less coherent, deflection attempts might be more effective than current calculations suggest. Either outcome would influence mission design for hypothetical future threats. The international cooperation demonstrated during Apophis observations will likely serve as a template for responding to genuine impact threats. The coordination between NASA, ESA, and observatories worldwide during the 2029 encounter represents the most comprehensive international effort ever undertaken for a single asteroid. This collaboration model could scale up to address confirmed hazards requiring deflection missions. The technical capabilities developed for Apophis characterization will continue benefiting the broader planetary defense program. Improved radar imaging techniques, more sensitive photometric measurements, and better computational models for orbital evolution all emerged from sustained focus on this one asteroid. These advances will apply to thousands of other near-Earth asteroids requiring detailed study. The Apophis encounter will also inform policy discussions about planetary defense governance and decision-making authority. While this specific asteroid poses no threat, it represents a test case for international cooperation in space safety. The procedures developed for coordinating observations and sharing data could prove essential when facing genuine impact hazards requiring rapid response. The educational impact of the Apophis story will likely persist for decades. The transformation from potential threat to confirmed safety case illustrates fundamental principles of scientific methodology, risk assessment, and evidence-based decision-making. These lessons extend far beyond asteroid science to broader questions about how society evaluates and responds to low-probability, high-consequence risks. Future asteroid discoveries will benefit from the infrastructure and protocols developed for Apophis characterization. The observational networks, computational tools, and international coordination mechanisms established during 20 years of Apophis research now operate continuously, providing early warning and risk assessment for newly discovered, potentially hazardous asteroids. The upcoming NEO Surveyor mission, scheduled for launch no earlier than late 2027, will dramatically accelerate the discovery of Apophis-class objects. This space-based infrared telescope will detect dark asteroids that are invisible to ground-based optical surveys, potentially revealing hundreds or thousands of previously unknown PHAs in the 140-meter to 500-meter size range. Each new discovery will undergo the same process of initial uncertainty, followed by gradual refinement that characterized Apophis research. Most will prove harmless upon detailed analysis, but statistical inevitability suggests that eventually, surveys will discover an object on a confirmed collision course with Earth. When that happens, the tools and procedures developed for Apophis will provide the foundation for humanity's response. The Vera C. Rubin Observatory, beginning operations in 2025, will contribute precise orbit determinations for thousands of near-Earth asteroids annually. The LSST survey's unprecedented combination of sky coverage, sensitivity, and observing cadence will eliminate most sources of orbital uncertainty that plagued early Apophis calculations. The technological advances driven by Apophis research will continue paying dividends for decades. Improved radar imaging capabilities at Goldstone and Greenbank can now resolve asteroid surface features at meter-level resolution. Enhanced optical tracking systems provide astrometric measurements precise enough to detect the subtle orbital drift caused by the Yarkovsky effect. These capabilities represent permanent improvements to humanity's planetary defense infrastructure. The data collected during and after the 2029 encounter will likely reveal surprises about asteroid physics that current models don't anticipate. The behavior of rubble pile structures under tidal stress remains poorly understood, and Apophis represents our first opportunity to study this phenomenon directly. Any unexpected responses could reshape theoretical understanding of asteroid mechanics. Commercial space activities may also benefit from Apophis research. Private companies are increasingly interested in asteroid mining and resource extraction activities that require detailed knowledge of asteroid structure and composition. The characterization techniques developed for Apophis could inform future commercial missions to near-Earth asteroids. The encounter may also influence public policy discussions about space exploration priorities and funding allocation. The successful transformation of Apophis from threat to scientific opportunity demonstrates the value of sustained investment in asteroid research and planetary defense capabilities. This success story could justify expanded funding for related programs. International space law and governance frameworks may evolve in response to lessons learned from Apophis coordination. The asteroid story highlights both the importance of international cooperation in planetary defense and the current lack of formal mechanisms for coordinating responses to confirmed impact threats. Future policy development may address these gaps. The amateur astronomy community will likely maintain interest in Apophis long after the 2029 encounter. The asteroid will remain an accessible target for small telescopes, providing ongoing opportunities for citizen science contributions to professional research. These observations could detect long-term changes in the asteroid's properties triggered by the Earth encounter. Educational institutions worldwide are developing long-term curriculum materials based on the Apophis case study. The asteroid story provides an ideal framework for teaching orbital mechanics, statistical analysis, scientific methodology, and risk communication. These educational resources will benefit students for decades to come. The psychological and cultural impact of Apophis may prove as significant as its scientific contributions. The asteroid's transformation from harbinger of doom to harmless spectacle demonstrates humanity's growing capability to understand and manage cosmic risks. This represents a fundamental shift from passive vulnerability to active planetary stewardship. Future asteroid missions will likely target objects with similar characteristics to Apophis, taking advantage of the detailed knowledge base developed through decades of observation. The asteroid serves as a prototype for the potentially hazardous asteroid population, making it an ideal comparison case for understanding other PHAs. The timing of technological developments may prove fortuitous for applying Apophis lessons to genuine threats. The DART mission validated kinetic impactor technology just a few years before the Apophis encounter, while OSIRIS-APEX will provide detailed post-encounter data that can inform future deflection mission designs. This convergence of capabilities represents unprecedented readiness for planetary defense applications. Speculation about unexpected discoveries during the encounter adds another layer of anticipation to the scientific community. If Earth's tidal forces trigger more dramatic changes in Apophis than predicted, those observations could revolutionize understanding of asteroid internal structure and mechanical properties. Even negative results, no significant changes, would provide valuable constraints on theoretical models. The global nature of the observation campaign will likely establish new standards for international scientific cooperation. The coordination protocols developed for Apophis could serve as templates for other large-scale astronomical projects requiring worldwide participation. The success of this collaboration may influence how the scientific community approaches future challenges. The economic implications of Apophis research extend beyond direct scientific benefits to broader questions about the value of planetary defense investments. The transformation from potential catastrophe to controlled scientific opportunity represents an enormous return on the relatively modest investments made in asteroid surveys and characterization over the past 2 decades. Public engagement efforts will likely continue long after the encounter, as educators and outreach specialists use the Apophis story to illustrate principles of scientific literacy and evidence-based thinking. The asteroid's narrative arc from threat to safety provides a compelling case study in how scientific understanding evolves through systematic observation and analysis. The technical infrastructure developed for Apophis observations will remain available for studying other asteroids, multiplying the return on investment in specialized equipment and expertise. Radar systems, optical telescopes, and data analysis tools optimized for asteroid characterization will continue serving the planetary defense mission for decades. Future historians may mark the Apophis encounter as a turning point in humanity's relationship with cosmic hazards. The asteroid story demonstrates that with sufficient time, resources, and international cooperation, apparent existential threats can be transformed into opportunities for scientific advancement and public education. The encounter will likely inspire the next generation of planetary scientists and aerospace engineers. Young people who witness Apophis's safe passage and the scientific discoveries that follow may choose careers dedicated to protecting Earth from future cosmic threats. This human capital development represents another long-term benefit of the asteroid's scientific legacy. As we look beyond 2029, toward the remainder of the 21st century, the Apophis encounter will likely be remembered as the moment when planetary defense matured from reactive crisis management to proactive threat assessment and mitigation. The asteroid that once threatened to end civilization may ultimately be remembered as the object that taught us how to defend it. But even as we prepare to celebrate humanity's growing mastery over cosmic hazards, the Apophis story contains a sobering reminder. For all our technological advancement and international cooperation, we remain vulnerable to the fundamental forces that have shaped planetary evolution for billions of years. The question isn't whether another potentially threatening asteroid will be discovered, but when, and whether the lessons learned from Apophis will prove sufficient to meet that challenge. The real legacy of Apophis may not be the scientific data it provides, or the public engagement it inspires, but the institutional frameworks and technical capabilities it helped create. These tools and procedures represent humanity's insurance policy against cosmic catastrophe, an investment in survival that we hope never to need, but cannot afford to lack. Part 15, Finale. The real threat isn't 3IATLAS, it's complacency. As 3IATLAS fades into the interstellar void and Apophis prepares for its historic encounter with Earth, we find ourselves at a crossroads in humanity's relationship with cosmic hazards. The contrast between these two objects illuminates not just the difference between spectacular and dangerous, but between the threats we notice and the ones that actually matter. 3IATLAS represents everything we find compelling about the universe. Mystery, rarity, the romance of interstellar travel. It arrives, trailing a glowing coma visible to backyard telescopes, generates thousands of research papers and news articles, and disappears forever into the darkness between stars. It's beautiful, fascinating, and completely irrelevant to human survival. Apophis embodies the opposite qualities: familiarity, predictability, the mundane reality of gravitational mechanics. It follows the same elliptical orbit it has traced for millions of years, composed of ordinary rock and metal, distinguishable from thousands of similar asteroids only by the accident of its discovery timing and the brief period when we thought it might kill us all. Yet, Apophis taught us everything important about planetary defense, while 3IATLAS teaches us nothing except the composition of materials from distant stellar systems. The exotic visitor captures our imagination. The ordinary neighbor could have ended our civilization. This distinction matters because it reveals a fundamental flaw in how humans assess risks. We're drawn to the novel, the mysterious, the unprecedented, even when these phenomena pose no actual danger. Meanwhile, we ignore or minimize familiar threats that accumulate quietly in the background, building toward potential catastrophe through the patient mathematics of probability. The space hazard landscape extends far beyond asteroids to illustrate the sun's natural cycle. Orbital debris threatens every spacecraft in Earth orbit and grows more dangerous each year, but it lacks the dramatic appeal of asteroid impacts or alien visitors. Even among asteroid threats, public attention focuses disproportionately on the wrong targets. Extinction-level impacts by kilometer-sized objects dominate popular discussions, despite representing the lowest probability threats in the near-Earth asteroid population. The city-killer asteroids in the 100 to 500 meter size range pose much higher cumulative risks, but generate less interest because their consequences are merely regional rather than global. This misallocation of attention has policy implications that extend beyond academic discussions of risk assessment. Public funding for planetary defense competes with other priorities, and that competition is influenced by public perception of threats. Exotic but harmless visitors like 3IATLAS generate public interest that could be redirected toward genuine hazards if properly channeled by science communicators and policymakers. The success story of Apophis demonstrates what's possible when the scientific community takes near-Earth asteroid threats seriously. The transformation from potential catastrophe to confirmed safety required decades of sustained observation, international cooperation, and technological development. The same infrastructure that eliminated the Apophis threat now operates continuously, providing early warning for future hazards. But this infrastructure exists only because previous generations of astronomers and policymakers recognized the importance of mundane threats over spectacular ones. They understood that protecting civilization required systematic surveys of ordinary asteroids, not occasional studies of exotic visitors. They invested in ground-based telescopes, radar facilities, and data analysis systems optimized for detecting and tracking near-Earth objects. The upcoming NEO Surveyor mission represents the next phase of this systematic approach. Unlike missions designed to study specific exotic objects, NEO Surveyor is optimized for discovering large numbers of ordinary, potentially hazardous asteroids. Its success will be measured not by the uniqueness of its discoveries, but by the completeness of its catalog. The Vera C. Rubin Observatory embodies the same philosophy. Wide-area surveys, designed to find and track thousands of near-Earth asteroids, rather than detailed studies of individual objects. LSST will likely discover more asteroids in its first year of operation than all previous surveys combined, filling critical gaps in our knowledge of the PHA population. This systematic approach stands in stark contrast to the episodic attention generated by objects like Oumuamua. The interstellar comet will be studied intensively for a few months, generate a burst of scientific papers and media coverage, then fade from public consciousness as it disappears into space. The steady work of planetary defense continues regardless of whether exotic visitors are present to attract attention. The DART mission exemplifies the practical focus of modern planetary defense. Rather than attempting to deflect the most spectacular or mysterious asteroid, DART targeted an ordinary near-Earth asteroid system selected specifically because it offered the best opportunity to validate deflection technology. The mission's success provides confidence that similar techniques could work against genuine threats. International cooperation frameworks like the International Asteroid Warning Network and Space Mission Planning Advisory Group focus on mundane but essential coordination tasks. Standardizing observation procedures, sharing data across borders, developing response protocols for confirmed threats. These organizations do not generate headlines, but they provide the institutional foundation for effective planetary defense. The communication challenges surrounding objects like Oumuamua and Apophis reveal another dimension of the complacency threat. Media coverage consistently emphasizes the exotic over the important, the spectacular over the significant. Science communicators must work actively to redirect public attention from harmless curiosities toward genuine hazards. The educational opportunities presented by high-profile encounters like Apophis's 2029 flyby should be leveraged to build lasting scientific literacy rather than temporary fascination. The goal is creating a public that can distinguish between legitimate concerns and sensationalized narratives, between statistical possibilities and credible threats. The economic dimensions of planetary defense also favor systematic approaches over episodic responses. The cost of comprehensive asteroid surveys and deflection technology development is modest compared to the potential consequences of a successful impact. But these investments must be sustained over decades to be effective, requiring public and political support that transcends the attention cycles of individual objects. The technological capabilities developed for planetary defense applications often benefit other areas of space science and exploration. The radar systems used to characterize near-Earth asteroids also support spacecraft navigation and planetary geology research. The orbital mechanics software developed for impact risk assessment enables mission design for robotic and human exploration. Looking toward the future, the greatest threat to effective planetary defense may not be a specific asteroid, but the gradual erosion of public and political support for systematic threat assessment and mitigation capabilities. The success in eliminating apparent threats like Apophis could breed complacency about future risks, leading to reduced funding and attention for ongoing survey and characterization efforts. The lesson of Oumuamua versus Apophis extends beyond planetary defense to broader questions about how modern societies identify and respond to emerging risks. Climate change, pandemic disease, technological disruption, all represent familiar, ongoing challenges that lack the dramatic appeal of more exotic but less probable threats. The space environment offers a unique laboratory for studying risk assessment and mitigation because the physics is well understood and the consequences are clearly defined. The lessons learned from planetary defense could inform approaches to other long-term threats facing human civilization. As Oumuamua disappears into the cosmic darkness, and Apophis approaches its date with scientific destiny, we are left with a fundamental choice about how to allocate our attention and resources. We can continue chasing exotic curiosities that pose no threat, or we can focus on the mundane but genuine hazards that patience and probability will eventually deliver to our doorstep. The universe does not care about our preference for spectacular over significant, exotic over ordinary, mysterious over mundane. Asteroids follow the laws of physics, not the laws of public relations. Our survival depends on understanding this difference and acting accordingly. The real threat is not the beautiful visitor from another star. It is the complacency that beautiful visitors can breed about the ordinary neighbors, whose behavior we can predict, track, and ultimately control. The choice between wonder and wisdom need not be exclusive. But when survival is at stake, wisdom must prevail. In the end, the most profound discovery about Oumuamua may be what it reveals about ourselves. Our attraction to the exotic, our neglect of the ordinary, and our ongoing struggle to align our instincts with the mathematical realities of existence in a universe that remains, despite our growing knowledge, fundamentally indifferent to our survival.